This search for alien life represents our deepest curiosity about our place in the cosmos, a gentle exploration that has evolved from ancient mythology through scientific revolution to today's sophisticated technological endeavors, each step bringing new understanding while deepening the beautiful mystery of whether we share this vast universe with other thinking beings. The search for alien life didn't begin with radio telescopes or space probes, but rather in the quiet moments when early humans sat beneath pristine night skies, unmarred by artificial light, and contemplated the countless points of light scattered across the darkness. These ancient observers, living thousands of years before our modern era, possessed the same fundamental curiosity that drives today's scientists, though they expressed their wonder through different languages of myth, philosophy, and early observation. In ancient Mesopotamia, where civilization first flourished between the Tigris and Euphrates rivers, astronomers meticulously tracked celestial movements on clay tablets, recording not just the paths of planets and stars, but also pondering what these distant lights might represent. The Babylonians, with their sophisticated mathematical systems, calculated planetary orbits with remarkable precision, and within their epic literature, we find hints of cosmic plurality. The Epic of Gilgamesh speaks of distant realms and beings beyond Earth, suggesting that even in humanity's earliest written stories, we imagined we might not be alone. The ancient Greeks transformed these mythological wonderings into philosophical inquiry. Anaximander, living in the 6th century before the Common Era, proposed that the cosmos contained infinite worlds, each potentially harboring life. His student Anaximenes expanded on this idea, suggesting that air, the breath of life on Earth, might exist throughout the universe, making other worlds capable of supporting beings like ourselves. These weren't mere flights of fancy but serious philosophical propositions based on logical reasoning about the nature of existence. Democritus, the atomist philosopher, took these ideas even further. He argued that since atoms combine in countless ways to create everything we observe, and since the universe contains infinite atoms, there must logically be infinite worlds, many of them inhabited. His writings, preserved only in fragments quoted by later authors, reveal a sophisticated understanding that the same natural processes operating on Earth could function elsewhere in the cosmos. This atomic theory of multiple worlds represented one of humanity's first scientific arguments for extraterrestrial life, based not on wishful thinking but on logical deduction from observed principles. The Roman philosopher Lucretius, in his poem De Rerum Natura, beautifully articulated these Greek ideas for a Latin audience. He wrote of countless worlds beyond our own, comparing them to dust motes dancing in a sunbeam, each potentially carrying its own forms of life. His verses, meant to be read aloud in the gentle rhythm of Latin poetry, carried these profound ideas through the centuries, preserving them through the fall of Rome and into the medieval period. In ancient China, astronomers of the Han Dynasty developed their own sophisticated understanding of the cosmos. They spoke of the universe as infinite, filled with celestial bodies too distant to see. The philosopher Wang Chong, writing in the 1st century of the Common Era, explicitly stated that the heavens contained other worlds with their own inhabitants. Chinese astronomical texts describe the universe as a limitless ocean of qi, or life energy, within which countless worlds form and dissolve like bubbles, each potentially harboring conscious beings. The Mayan civilization of Mesoamerica developed perhaps the most sophisticated pre-telescopic astronomy in human history. Their precise calculations of planetary movements and their complex calendar systems suggest a deep engagement with cosmic questions. Mayan creation myths speak of multiple world ages and various attempts by the gods to create intelligent life, implying a universe where consciousness might take many forms across different cosmic epochs. In India, ancient Sanskrit texts present a cosmos of stunning complexity and scale. The Vedas and Puranas describe countless universes, each with their own inhabitants, existing in endless cycles of creation and destruction. The concept of the multiverse, which modern physics now seriously considers, appears in these texts written thousands of years ago. Hindu and Buddhist cosmology populated these infinite worlds with diverse beings, from devas in higher realms to creatures in lower worlds, presenting a universe teeming with consciousness in various forms. Islamic scholars during the Golden Age of Islam made crucial contributions to this ancient dialogue. Al-Biruni, the 11th century polymath, wrote extensively about the possibility of other worlds, using both philosophical arguments and astronomical observations to support his ideas. He noted that Allah's creative power was limitless, making it logical that creation would extend beyond Earth. Ibn Rushd, known in the Latin world as Averroes, argued that Aristotle's rejection of other worlds was flawed, proposing instead that divine creativity would naturally produce multiple inhabited realms. These diverse cultural approaches to the question of alien life reveal something profound about human nature itself. Across continents and millennia, separated by vast distances and cultural differences, humans have independently arrived at the same fundamental question and often similar answers. This convergent wondering suggests that the search for cosmic companionship represents something essential to human consciousness, a need to understand our place in the larger scheme of existence. The methods these ancient thinkers used to approach the question of alien life laid important groundwork for later scientific inquiry. They established several key principles that still guide our search today. First, they recognize that the same natural laws operating on Earth likely function throughout the universe, a principle we now call the cosmological principle. Second, they understood that the vast scale of the universe makes it statistically unlikely that Earth alone harbors life. Third, they grasped that life might take forms very different from what we observe on Earth, adapted to different environments and conditions. The transition from ancient philosophy to scientific speculation about alien life began during the Renaissance, a period when European thought underwent radical transformation. The rediscovery of ancient Greek and Roman texts, combined with new astronomical observations and mathematical tools, created an intellectual revolution that fundamentally changed how humanity approached the question of extraterrestrial life. Nicholas Copernicus, though cautious in his published works, initiated a cosmic revolution by displacing Earth from the center of the universe. His heliocentric model, published in 1543 as De Revolutionibus Orbium Coelestium, did more than rearrange the solar system, it demoted Earth from a unique, central position to just one planet among others orbiting the Sun. This shift carried profound implications for the possibility of alien life. If Earth was not the center of creation but merely one world among many, why should life be unique to our planet? Giordano Bruno, the Italian philosopher and cosmologist, took the Copernican revolution to its logical extreme. In his work De L'Infinito, Universo e Mondi, published in 1584, Bruno proposed an infinite universe filled with countless stars, each a sun like our own, surrounded by inhabited planets. His vision was breathtaking in scope, describing a cosmos where every star nurtures worlds teeming with life, each developing according to its own conditions and divine plan. Bruno's ideas went far beyond what astronomical observations could support at the time, but his passionate advocacy for cosmic plurality inspired generations of thinkers. Bruno paid the ultimate price for his radical ideas. The Roman Inquisition condemned him for heresy, and in 1600, he was burned at the stake in Rome's Campo de' Fiori. While his execution resulted from various theological disputes, not solely his belief in other worlds, his martyrdom became symbolic of the conflict between free scientific inquiry and religious orthodoxy. His death cast a long shadow over discussions of extraterrestrial life, making many subsequent thinkers more cautious in their speculations. Johannes Kepler, the brilliant mathematician and astronomer, approached the question of alien life with characteristic precision and imagination. His discovery of the laws of planetary motion revolutionized astronomy, but he also wrote extensively about the possibility of lunar inhabitants. In his Somnium, published posthumously in 1634, Kepler created what many consider the first work of science fiction, describing a journey to the moon and its possible inhabitants. Though framed as a dream to avoid controversy, Kepler's work seriously considered how life might adapt to lunar conditions, with longer days and nights, extreme temperature variations, and lower gravity. Kepler's correspondence reveals his deep engagement with the question of extraterrestrial life. Writing to Galileo, he expressed excitement about the telescopic discovery of Jupiter's moons, seeing them as evidence that the cosmos was arranged for inhabitants throughout, not just Earth observers. He reasoned that Jupiter's moons would serve no purpose unless Jupiter itself was inhabited, as they would be invisible to Earth-bound observers without telescopes. This anthropic reasoning, while flawed by modern standards, shows how seriously Kepler took the possibility of alien life. Galileo Galilei's telescopic observations beginning in 1609 transformed speculation into observation-based science. His discovery of mountains and valleys on the moon showed it was a world like Earth, not a perfect crystalline sphere as Aristotelian philosophy claimed. The 4 moons orbiting Jupiter demonstrated that celestial bodies could orbit centers other than Earth, supporting the Copernican model and suggesting a universe with multiple systems. His observation of countless previously invisible stars implied a cosmos far vaster than previously imagined, filled with potential homes for life. Though Galileo remained cautious about explicitly endorsing the existence of alien life, his discoveries made such ideas increasingly plausible. His telescopic observations of the Milky Way, resolving it into countless individual stars, suggested a universe of staggering scale. In his Dialogue Concerning the Two Chief World Systems, Galileo had his character Segredo marvel at the possibility of countless other worlds, though he carefully attributed such speculation to the character rather than stating it as his own belief. René Descartes, the father of modern philosophy, developed a mechanical view of the universe that profoundly influenced thinking about extraterrestrial life. His vortex theory of planetary motion, though later proven wrong, proposed that every star was surrounded by a whirlpool of matter that could form planets. This mechanical model suggested that planet formation was a natural, inevitable process throughout the universe, not a unique event requiring special divine intervention. Descartes privately believed in the existence of extraterrestrial life but was cautious about publishing these views, mindful of Bruno's fate and Galileo's condemnation. In letters to colleagues, he expressed the opinion that it would limit God's power to suggest life existed only on Earth. His mechanical philosophy implied that the same physical processes operating on Earth would function throughout the universe, making life a natural consequence of proper conditions rather than a miracle. Christian Huygens, the Dutch astronomer and physicist, wrote one of the most influential early works on extraterrestrial life. His Cosmotheoros, published in 1695, systematically examined the conditions necessary for life and argued for its presence throughout the solar system and beyond. Huygens applied rigorous scientific reasoning, considering factors like planetary temperatures, the presence of water, and atmospheric conditions. He argued that God would not create vast worlds only to leave them empty, combining theological and scientific arguments in a way that appealed to his contemporary audience. Huygens made specific predictions about alien life based on physical principles. He calculated that Jupiter and Saturn, despite their distance from the Sun, could support life because their inhabitants might be adapted to cold, just as Earth creatures adapt to various climates. He suggested that aliens would have sensory organs to perceive their environment, limbs for manipulation, and intelligence to understand nature's laws. His systematic approach established a template for scientific speculation about alien life that influenced researchers for centuries. Bernard Le Bovier de Fontenelle popularized these scientific ideas in his Entretiens sur la pluralité des mondes, published in 1686. Written as a series of conversations between a philosopher and a marquise, the book made complex astronomical ideas accessible to general readers, particularly women excluded from formal scientific education. Fontenelle's work reached a vast audience, going through numerous editions and translations, spreading the idea of alien life throughout European intellectual culture. Fontenelle's gentle, conversational style made cosmic plurality seem not just possible but probable, even inevitable. He described inhabitants of different planets adapted to their specific conditions, Mercurians quick and volatile due to their planet's heat and rapid orbit, Saturnians slow and contemplative in their cold, distant world. While these descriptions were fanciful, they introduced the important concept that life would adapt to local conditions, a principle central to modern astrobiology. Isaac Newton's revolutionary physics provided a new framework for understanding the universe that made extraterrestrial life seem more plausible. His law of universal gravitation showed that the same force governing falling apples on Earth also controlled planetary orbits and stellar motions. This universal application of physical laws suggested that if life arose from natural processes on Earth, similar processes could produce life elsewhere under suitable conditions. Newton himself remained cautious about speculating on alien life, focusing on mathematical and physical principles. However, his followers, particularly Richard Bentley, used Newtonian physics to argue for cosmic plurality. Bentley's Boyle lectures, delivered in 1692, used Newton's discoveries to argue that the vast spaces between stars made sense only if they separated inhabited solar systems, preventing gravitational interference between different worlds' orbits. The scientific revolution's impact on thinking about extraterrestrial life extended beyond astronomy and physics. Advances in microscopy revealed previously invisible worlds of microorganisms, demonstrating that life existed in forms and places previously unimagined. Antony van Leeuwenhoek's discoveries of bacteria and protozoa showed that life's diversity exceeded human imagination, making it easier to conceive of radically different forms of life on other worlds. The 20th century brought a paradox that would fundamentally reshape humanity's search for extraterrestrial intelligence. As our understanding of the universe's vast scale became clearer and our technology grew more sophisticated, a troubling question emerged from a casual lunchtime conversation that would echo through decades of scientific inquiry. This question, posed by physicist Enrico Fermi in 1950, crystallized centuries of speculation into a sharp challenge that continues to perplex scientists today. The setting was Los Alamos National Laboratory, where some of the world's brightest minds had gathered in the aftermath of the Manhattan Project. During a routine lunch break, Fermi and his colleagues Edward Teller, Herbert York, and Emil Konopinski were discussing recent UFO reports that had captured public imagination. The conversation meandered through various topics related to space travel and extraterrestrial life, touching on the feasibility of interstellar travel and the probability of alien civilizations. Then, in the middle of the meal, Fermi suddenly exclaimed, "Where is everybody?" This simple question, later formalized as the Fermi Paradox, encapsulated a profound cosmic mystery. Given the vast age of the universe, the enormous number of stars, and the growing evidence that planets were common, why had humanity detected no signs of alien civilizations? The universe should be teeming with life, yet it appeared silent. Fermi's reasoning was elegantly simple yet devastating in its implications. He calculated that even at modest speeds achievable with nuclear propulsion, a civilization could colonize the entire Milky Way galaxy in just a few million years. This might seem like an enormous time span, but compared to the galaxy's age of over 13 billion years, it represents less than 1% of cosmic history. Any civilization that arose even slightly earlier than humanity should have had ample time to spread throughout the galaxy, yet we see no evidence of such expansion. The paradox grew sharper as astronomers better understood the universe's scale. The Milky Way contains between 200 and 400 billion stars. Even if only a tiny fraction of these stars host habitable planets, and only a tiny fraction of those planets develop life, and only a tiny fraction of that life becomes intelligent, the sheer number suggests thousands or millions of civilizations should exist in our galaxy alone. Yet the cosmos appears empty of artificial signals, interstellar probes, or any signs of large-scale engineering projects that advanced civilizations might undertake. Michael Hart formalized Fermi's question in a 1975 paper that examined possible resolutions to the paradox. Hart argued that the absence of extraterrestrials on Earth today implies that no other technological civilizations exist in our galaxy. His reasoning was straightforward: given enough time, any spacefaring civilization would inevitably colonize every habitable system, driven by population pressure, curiosity, or simple mathematical expansion. The fact that aliens haven't colonized Earth suggests they don't exist. This conclusion, known as the Hart-Tipler argument after Frank Tipler expanded on it, sparked intense debate within the scientific community. Many researchers found it difficult to accept that humanity might be alone in the galaxy, given the vast number of potentially habitable worlds. The argument seemed to require that Earth be special in some fundamental way, contradicting the Copernican principle that had guided astronomy since the Renaissance. Various explanations for the Great Silence emerged, each with profound implications for humanity's future. Perhaps life itself is extraordinarily rare, requiring such an unlikely combination of conditions that Earth represents a cosmic fluke. This explanation, while solving the paradox, seems to require an uncomfortable degree of cosmic coincidence. The discovery of extremophiles thriving in Earth's most hostile environment suggests life is remarkably adaptable and resilient, making its complete absence elsewhere seem unlikely. Another possibility is that simple life is common, but complex, intelligent life is vanishingly rare. The evolution from single-celled organisms to complex multicellular life took billions of years on Earth, and many critical steps in this process might have been highly improbable events. The development of eukaryotic cells, sexual reproduction, multicellularity, and intelligence might each represent nearly insurmountable evolutionary hurdles that few planets ever overcome. The temporal aspect of the paradox adds another layer of complexity. Civilizations might typically destroy themselves shortly after developing technology capable of interstellar communication. Nuclear weapons, environmental destruction, artificial intelligence, or other existential risks might eliminate most civilizations before they can spread beyond their home systems. This sobering possibility, known as the Great Filter, suggests that the universe might be littered with the ruins of dead civilizations that never made it past a critical technological threshold. Carl Sagan and William Newman proposed a more optimistic resolution in 1983, suggesting that interstellar colonization might proceed much more slowly than Fermi assumed. They argued that population pressure wouldn't drive expansion once civilizations achieved sustainable population control, and that the vast distances between stars would make colonization economically prohibitive except under extraordinary circumstances. Their models showed that even small reductions in colonization probability or speed could result in large regions of the galaxy remaining uncolonized for billions of years. The zoo hypothesis, proposed by John Ball in 1973, offers a different perspective entirely. Perhaps advanced civilizations deliberately avoid contact with emerging species like humanity, maintaining Earth as a kind of nature preserve or laboratory. This cosmic quarantine might be enforced to allow natural cultural and technological development without outside interference. While this explanation seems to require an unrealistic degree of coordination among independent civilizations, it remains a logical possibility that cannot be definitively ruled out. Technological limitations might also explain the silence. Perhaps our methods of searching for alien signals are primitive, like looking for smoke signals in an age of radio communication. Advanced civilizations might communicate using neutrinos, gravitational waves, or quantum entanglement methods we haven't discovered. They might have moved beyond electromagnetic communication entirely, making our radio searches futile. The universe could be buzzing with alien conversations we simply cannot detect with current technology. The transcension hypothesis suggests that advanced civilizations might turn inward rather than outward, focusing on virtual realities, artificial intelligence, or other forms of existence that don't require physical expansion. They might compress themselves into increasingly small spaces to maximize computational efficiency, becoming invisible to outside observers. This inward turn might be a natural evolutionary path for intelligence, making the physical universe seem empty while consciousness flourishes in dimensions we cannot perceive. Distance and time present fundamental challenges to detecting alien civilizations. The nearest star system, Proxima Centauri, lies over 4 light-years away, meaning any signal takes years to traverse even this cosmic neighborhood. Civilizations might rise and fall in cosmic eye blinks, their brief transmissions passing Earth before humans evolved or after we've gone extinct. The synchronicity problem suggests that two civilizations must not only exist simultaneously but also at compatible technological levels, a coincidence that might be extraordinarily rare. Recent discoveries have added new dimensions to Fermi's paradox. The detection of thousands of exoplanets shows that planetary systems are common, with many worlds orbiting within their stars' habitable zones. Some of these planets are significantly older than Earth, giving potential life billions of additional years to evolve. The discovery of potentially habitable worlds like Kepler 452b, often called Earth's cousin, makes the absence of detectable civilizations even more puzzling. The study of extremophiles on Earth has expanded our concept of habitability, suggesting life might exist in environments previously thought sterile. Organisms thriving in boiling water, surviving in Antarctic ice, or living miles underground show that life is remarkably adaptable. If life can survive in such extreme conditions on Earth, similar or even more exotic environments on other worlds might also harbor living organisms. This expanded habitability makes the apparent absence of life even more mysterious. In 1961, astronomer Frank Drake developed an elegant mathematical framework that would transform the search for extraterrestrial intelligence from philosophical speculation into quantitative science. The Drake equation, as it became known, doesn't provide a definitive answer to whether alien civilizations exist, but rather organizes our ignorance into manageable components, each representing a crucial factor in the cosmic calculation of intelligence. Drake formulated his equation while preparing for the first scientific meeting on the search for extraterrestrial intelligence, held at the Green Bank Observatory in West Virginia. He needed a systematic way to organize the discussion, breaking down the enormous question of alien life into smaller, more tractable problems. The equation he developed became the meeting's agenda and subsequently the foundation for decades of scientific research into extraterrestrial intelligence. The equation multiplies 7 factors together to estimate the number of actively communicating civilizations in our galaxy. Each factor represents a step in the long journey from star formation to interstellar communication. The beauty of Drake's approach lies not in providing precise answers but in identifying what we need to know and quantifying our uncertainty about each crucial step in the development of communicating civilizations. The first factor, R star, represents the rate of star formation in our galaxy. When Drake first proposed his equation, astronomers estimated that about 1 new star formed per year in the Milky Way. Modern observations using infrared telescopes that can peer through cosmic dust have refined this estimate to approximately 1 to 3 solar masses of new stars annually. This translates to roughly 7 new stars per year when accounting for the predominance of smaller stars. This stellar birth rate has varied throughout cosmic history, with peaks of intense star formation billions of years ago gradually declining to today's more modest rate. Understanding star formation requires delving into the complex processes occurring within giant molecular clouds, vast regions of gas and dust where gravity slowly gathers material into increasingly dense clumps. These stellar nurseries, like the famous Orion Nebula, can spawn hundreds or thousands of stars from a single cloud. The process takes millions of years, with protostars gradually accumulating mass while clearing their orbital neighborhoods of debris. Not all stars are suitable for life as we understand it. Massive stars burn too quickly, giving insufficient time for biological evolution, while the smallest red dwarfs might have other challenges we're only beginning to understand. The second factor, Fp, represents the fraction of stars that have planetary systems. When Drake first proposed his equation, no planets outside our solar system had been confirmed, making this factor highly speculative. The situation has transformed dramatically with the discovery of thousands of exoplanets. Current estimates suggest that virtually every star hosts at least one planet, with many stars surrounded by complex multiplanet systems. The Kepler Space Telescope's observations indicate that planetary formation is a natural consequence of star formation, not a rare accident. The process of planetary formation is now understood as an inevitable byproduct of stellar birth. As a protostar forms from a collapsing gas cloud, conservation of angular momentum creates a rotating disk of material around the young star. Within this protoplanetary disk, dust grains collide and stick together, gradually building up from microscopic particles to mountain-sized planetesimals and eventually to full-sized planets. This process, called accretion, appears to be remarkably efficient, converting most available solid material into planets within a few million years. The third factor, Ni, estimates the average number of planets per solar system that could potentially support life. This factor depends critically on how we define habitability. The traditional approach focuses on the habitable zone, the region around a star where liquid water could exist on a planet's surface. For stars like our Sun, this zone extends roughly from Venus's orbit to Mars's orbit, though the exact boundaries depend on atmospheric composition and other factors. In our solar system, Earth sits comfortably within this zone, Mars occupies its outer edge, and Venus, despite being within the zone, became uninhabitable due to a runaway greenhouse effect. Modern understanding of habitability has expanded beyond the traditional habitable zone. Jupiter's moon Europa and Saturn's moon Enceladus maintain liquid water oceans beneath their icy surfaces, heated by tidal forces rather than stellar radiation. These discoveries suggest that habitable environments might exist far from the traditional habitable zone, dramatically increasing the number of potentially life-bearing worlds. Some researchers propose that rogue planets, ejected from their stellar systems and wandering through interstellar space, might maintain habitable conditions through radioactive heating and thick hydrogen atmospheres. The fourth factor, Fl, represents the fraction of suitable planets where life actually develops. This might be the most uncertain factor in Drake's equation because we have only one example of life's emergence, Earth. Life appeared on Earth remarkably quickly in geological terms, possibly within a few 100 million years of the planet's formation. This rapid appearance suggests that life might emerge readily when conditions are suitable, but drawing statistical conclusions from a single data point remains problematic. Laboratory experiments have shown that complex organic molecules, the building blocks of life, form readily under conditions thought to exist on early Earth. The famous Miller-Urey experiment in 1953 demonstrated That amino acids could form from simple gases when exposed to electrical discharges simulating lightning. Subsequent experiments have produced even more complex organic molecules, including nucleotides that form DNA and RNA. These results suggest that the chemical precursors of life are easily produced, though the step from complex chemistry to self-replicating life remains mysterious. The discovery of life in Earth's most extreme environments has expanded our concept of suitable conditions. Organisms thriving near deep-sea volcanic vents, in highly acidic pools, within solid rock miles underground, and in the dry valleys of Antarctica show that life is remarkably adaptable. These extremophiles suggest that life might exist in environments previously thought completely hostile, potentially increasing the value of FL substantially. The fifth factor, phi, estimates the fraction of life-bearing planets where intelligent life evolves. Intelligence, at least as humans define it, appears to be rare even on Earth. Our planet hosted life for over 3 billion years before producing a species capable of radio communication. The evolution of intelligence requires not just complex brains but also manipulative appendages, social structures that reward cooperation, and environmental pressures that favor problem-solving over simpler survival strategies. The evolution of human intelligence involved numerous contingent events that might not be repeated elsewhere. The asteroid impact that eliminated dinosaurs 66 million years ago opened ecological niches for mammals to diversify. Climate changes in Africa created mixed woodland savanna environments that may have driven our ancestors to develop bipedalism and larger brains. The development of language, possibly linked to specific genetic mutations, enabled complex cultural transmission of knowledge. Each of these steps might be improbable, making intelligence a rare outcome even on life-bearing worlds. However, convergent evolution on Earth suggests that certain features arise independently when they provide survival advantages. Eyes evolved separately in numerous lineages, as did flight, echolocation, and social behavior. Intelligence has emerged to varying degrees in primates, cetaceans, elephants, corvids, and cephalopods, suggesting that given sufficient time and appropriate selection pressures, intelligence might be a natural evolutionary outcome rather than a unique fluke. The sixth factor, FC, represents the fraction of intelligent civilizations that develop technology capable of interstellar communication. This factor highlights the distinction between intelligence and technological civilization. Dolphins and whales may possess considerable intelligence, but their aquatic environment prevents them from developing fire, metallurgy, or electronics. A planet dominated by intelligent but non-technological species would remain invisible to our searches. Human technological development required numerous prerequisites beyond intelligence. Agriculture enabled food surpluses that supported specialized roles beyond food production. Writing allowed knowledge accumulation across generations. Scientific methodology provided a systematic approach to understanding nature. The development of electromagnetic technology, from basic electrical experiments to radio transmitters, took humanity only a few centuries but required a specific sequence of discoveries that might not be inevitable. Cultural factors profoundly influence technological development. Ancient Greece developed sophisticated mathematics and philosophy but didn't industrialize. China invented gunpowder, printing, and navigation technologies centuries before Europe but didn't experience an industrial revolution. These historical examples suggest that technological development depends on complex interactions between environmental resources, social structures, economic systems, and cultural values that might combine differently on other worlds. The seventh and final factor, L, represents the average lifetime of a communicating civilization. This factor might ultimately dominate the equation's outcome. A civilization that broadcasts for only a century contributes little to the galactic community, while one that maintains communication for millions of years dramatically increases the probability of contact. Humanity has been broadcasting radio signals for roughly a century, a cosmic eye blink that highlights how brief our own contribution has been so far. The lifetime of civilizations depends on their ability to overcome existential challenges. Nuclear warfare, environmental destruction, pandemic diseases, asteroid impacts, and emerging technologies like artificial intelligence or nanotechnology all pose potential extinction risks. Civilizations might typically self-destruct shortly after developing powerful technologies, making L tragically short. Alternatively, civilizations that survive these challenges might become essentially immortal, spreading across multiple star systems and becoming resistant to local catastrophes. When Drake and his colleagues first estimated values for each factor at the Green Bank meeting, they arrived at numbers ranging from 1,000 to 100 million communicating civilizations in our galaxy. These enormous uncertainties reflect our profound ignorance about many crucial factors. Modern estimates vary even more widely, with pessimists calculating that we might be alone in the galaxy while optimists suggest millions of civilizations might exist. The Drake equation's true value lies not in calculating a specific number but in providing a framework for organizing research. Each factor represents a scientific discipline: stellar astronomy, planetary science, biology, evolution, sociology, and technology. Progress in any field refines our estimates and brings us closer to understanding our cosmic context. The equation transforms an impossibly large question into manageable research programs, each contributing to the larger puzzle. Recent discoveries have refined several factors significantly. The Kepler mission showed that planets are ubiquitous, essentially setting FP close to 1. The discovery of numerous potentially habitable exoplanets suggests NE might be around 0.2 to 0.5 for Sun-like stars. The rapid appearance of life on Earth and the discovery of extremophiles hints that FL might be relatively high, perhaps 0.1 or greater. However, factors related to intelligence and technology remain highly uncertain. The transformation of humanity's ancient quest to find cosmic companions into a systematic scientific endeavor began with a simple observation about the nature of radio waves and their potential for interstellar communication. In 1959, physicists Giuseppe Cacconi and Philip Morrison published a groundbreaking paper in the journal Nature that would launch the modern search for extraterrestrial intelligence. Their insight was elegantly straightforward yet revolutionary. Radio waves travel at the speed of light, pass relatively unimpeded through interstellar dust and gas, and require modest amounts of energy to transmit across cosmic distances. Cacconi and Morrison recognized that any technological civilization would likely discover radio waves as a natural consequence of understanding electromagnetism. These waves offer an ideal medium for interstellar communication, particularly at certain frequencies where natural cosmic noise is minimal. They identified the hydrogen line at 1420 MHz as especially promising. Hydrogen, the universe's most abundant element, emits radiation at this precise frequency, making it a universal marker that any astronomically aware civilization would know. They reasoned that alien civilizations might choose this frequency as a cosmic meeting place, a natural channel where different species might search for one another. Frank Drake, then a young astronomer at the National Radio Astronomy Observatory, independently reached similar conclusions. Without knowledge of Cacconi and Morrison's work, Drake had been planning humanity's first systematic search for alien radio signals. In 1960, using the 85-foot radio telescope at Green Bank, West Virginia, Drake launched Project Ozma, named after the Queen of L. Frank Baum's fictional land of Oz, a place populated by exotic and wonderful beings. Project Ozma targeted two nearby Sun-like stars, Tau Ceti and Epsilon Eridani, both roughly 11 light-years from Earth. Drake and his small team observed these stars for 4 months, scanning frequencies near the hydrogen line for any signs of artificial signals. The equipment was primitive by modern standards, capable of monitoring only a single frequency channel at a time, requiring painstaking manual tuning to search different frequencies. Despite these limitations, Project Ozma represented a profound conceptual leap, transforming the search for extraterrestrial intelligence from speculation into experimental science. The technical challenges facing early SETI researchers were formidable. Radio telescopes must distinguish potential alien signals from numerous sources of interference. Natural cosmic phenomena produce radio waves across the spectrum, from pulsars spinning hundreds of times per second to distant galaxies with active black holes at their centers. Earth-based technology creates an increasingly noisy electromagnetic environment, with satellites, cell phones, microwave ovens, and countless other devices producing signals that can overwhelm sensitive radio telescopes. Early SETI researchers had to develop sophisticated techniques to filter out these false alarms while remaining sensitive to genuine extraterrestrial signals. The search strategy itself posed fundamental questions that continue to challenge researchers today. Which frequencies should we monitor? The electromagnetic spectrum contains an infinite number of possible channels, and searching them all would take infinite time. Beyond the hydrogen line, researchers identified other magic frequencies based on universal physical constants. The hydroxyl radical broadcasts at 1667 MHz, and together with hydrogen's frequency, these boundaries define what some call the cosmic water hole, a quiet region of the spectrum between the emissions of hydrogen and hydroxyl, which together form water. The assumption that aliens would broadcast at these special frequencies reflects a deeper challenge in SETI. We must make assumptions about alien psychology and technology based solely on human experience. Perhaps advanced civilizations consider radio communication primitive, having moved on to technologies we haven't discovered. Maybe they deliberately avoid obvious frequencies to prevent detection by hostile civilizations. These uncertainties multiply the difficulty of an already challenging search. Project Ozma detected no confirmed alien signals, but it inspired a generation of researchers and demonstrated that SETI could be conducted with scientific rigor. The negative result itself provided valuable information, showing that at least 2 nearby stars weren't broadcasting powerful radio beacons at the observed frequencies during the observation period. This might seem like a modest achievement, but it represented humanity's first systematic attempt to test the hypothesis of communicating extraterrestrial civilizations. The Soviet Union developed its own extensive SETI programs during the 1960s and 70s, bringing different perspectives and techniques to the search. Soviet scientists, working within a dialectical materialist framework that viewed life and intelligence as natural outcomes of matter's evolution, were often more optimistic about extraterrestrial intelligence than their Western counterparts. Nikolai Kardashev proposed a classification system for civilizations based on their energy consumption that remains influential today. Kardashev's scale divides civilizations into 3 types based on their ability to harness energy. Type 1 civilizations control all energy available on their home planet, roughly 10 to the 16th watts for an Earth-like world. Type 2 civilizations harness their entire star's output, approximately 10 to the 26th watts for a Sun-like star. Type 3 civilizations control energy on a galactic scale, utilizing 10 to the 36th watts or more. Humanity currently ranks around 0.7 on this scale, not yet achieving full Type 1 status. This classification system profoundly influenced SETI strategies. Type 2 and 3 civilizations would be vastly easier to detect than Type 1 civilizations like ourselves. A Type 2 civilization might build a Dyson sphere, a massive structure surrounding their star to capture its entire energy output. Such a structure would be invisible in optical light but would glow brightly in infrared as it re-radiated the star's energy as waste heat. Type 3 civilizations might be detectable through their large-scale engineering projects, perhaps visible as anomalous distributions of stars or unusual galactic properties. Soviet SETI programs also emphasized optical searches alongside radio observations. While radio waves seem ideal for interstellar communication, laser technology offers certain advantages. Laser beams can be tightly focused, delivering more energy to a specific target with less power than omnidirectional radio broadcasts. Pulsed lasers can achieve enormous peak intensities, briefly outshining entire stars at specific wavelengths. Soviet astronomers searched for such laser pulses, though without success. The 1970s saw SETI efforts expand globally, with researchers developing increasingly sophisticated search strategies. The Ohio State University Radio Observatory conducted one of the longest-running SETI programs, continuously monitoring the sky from 1973 to 1995. On August 15, 1977, this program detected one of the most intriguing signals in SETI history, the famous WOW signal. Jerry Eman, a volunteer researcher analyzing data from the Big Ear radio telescope, noticed an extraordinarily strong narrowband signal that lasted 72 seconds, the maximum duration the telescope could observe any given point as Earth rotated. The signal was so striking that Eman wrote, "Wow," in red pen on the computer printout, giving the signal its enduring name. The signal appeared to originate from the direction of the constellation Sagittarius and exhibited characteristics expected from an extraterrestrial transmission. It was narrowband, appeared at a frequency near the hydrogen line, and showed no obvious terrestrial origin. Despite extensive follow-up observations, the WOW signal was never detected again. This non-repeatability frustrates scientists, who require reproducible observations to confirm discoveries. Various explanations have been proposed, from secret military satellites to reflections of terrestrial signals off space debris. Some suggest it might have been a one-time transmission from an alien civilization. Perhaps a beacon that happened to sweep past Earth only once during our observations. The WOW signal remains unexplained, a tantalizing hint of what SETI researchers hope to find but insufficient evidence to claim detection of extraterrestrial intelligence. NASA's involvement in SETI reached its peak with the planned High-Resolution Microwave Survey, later renamed the Microwave Observing Program to avoid the increasingly controversial SETI acronym. This ambitious project, developed through the 1980s, would have used the world's largest radio telescopes to conduct both targeted searches of sun-like stars and an all-sky survey for strong signals from any direction. The program incorporated advanced signal processing technology, capable of simultaneously analyzing millions of frequency channels for patterns suggesting artificial origin. The project began observations on October 12, 1992, the 500th anniversary of Columbus's arrival in the Americas, symbolically beginning humanity's search for new worlds. However, just 1 year later, Congress terminated funding, with Senator Richard Bryan declaring that, not a single Martian has yet been found. This political setback devastated American SETI efforts, though it also catalyzed private funding that would ultimately create more flexible and innovative programs. The SETI Institute, founded in 1984, emerged as the primary organization continuing the search after government funding ended. Private donations, particularly from technology entrepreneurs who understood the search's long-term significance, enabled SETI research to continue and even expand. Paul Allen, co-founder of Microsoft, provided funding for the Allen Telescope Array, designed specifically for SETI observations. This array, when fully constructed, will consist of 350 small radio dishes working together, providing unprecedented sensitivity and sky coverage. The development of digital signal processing revolutionized SETI capabilities. Early searches could monitor only single channels or small numbers of frequencies simultaneously. Modern SETI instruments can analyze billions of frequency channels in real time, searching for narrowband signals, pulses, drifting frequencies, and complex patterns that might indicate artificial origin. Machine learning algorithms increasingly assist in identifying interesting signals from the vast data streams, learning to recognize potential technosignatures while filtering out terrestrial interference. SETI at Home, launched in 1999, transformed public participation in the search for extraterrestrial intelligence. This distributed computing project allowed anyone with an internet-connected computer to contribute processing power to analyze radio telescope data. Millions of volunteers worldwide have participated, making SETI at Home one of the most successful citizen science projects ever undertaken. While it hasn't detected confirmed alien signals, it has demonstrated enormous public interest in the search and provided valuable computing resources that would otherwise be unaffordable. The philosophical implications of SETI extend far beyond the technical challenge of detecting signals. The search forces us to confront fundamental questions about intelligence, communication, and cosmic loneliness. What constitutes a message? How would we recognize intelligence utterly unlike our own? Should we actively transmit messages to potential alien civilizations, or does that pose an existential risk to humanity? These questions have sparked debates among scientists, philosophers, and the public. Active SETI, also called METI, messaging extraterrestrial intelligence, remains controversial within the scientific community. Some researchers argue that transmitting powerful signals to announce our presence is foolhardy, potentially attracting attention from hostile civilizations. Others contend that any civilization capable of interstellar travel would already know about Earth through our biosignatures, making radio broadcasts irrelevant to our safety. Several messages have been transmitted, including the famous Arecibo message of 1974, though these have been largely symbolic rather than sustained attempts at interstellar communication. The space age brought humanity's search for life beyond Earth into a new realm of direct exploration, transforming distant worlds from points of light into landscapes we could touch, analyze, and understand with unprecedented detail. This golden age of discovery began with tentative steps into our cosmic backyard and has progressively expanded our reach, each mission building upon previous discoveries while raising new questions about life's potential throughout the solar system. The Viking missions to Mars in 1976 represented humanity's first serious attempt to search for extraterrestrial life through direct exploration. These twin spacecraft, each consisting of an orbiter and lander, carried sophisticated laboratories designed specifically to detect living organisms in Martian soil. The ambition of sending biological laboratories to another planet, controlled remotely from Earth, represented an extraordinary technological achievement that would have seemed like pure fantasy just decades earlier. Viking's biological experiments were ingeniously designed to detect life as we understand it while remaining open to unexpected discoveries. The labeled release experiment added nutrients tagged with radioactive carbon to Martian soil samples, monitoring for carbon dioxide emissions that would indicate metabolic activity. The pyrolytic release experiment tested whether Martian organisms could incorporate carbon from the atmosphere, similar to photosynthesis on Earth. The gas exchange experiment looked for changes in atmospheric composition when soil was exposed to water vapor and nutrients. The results from these experiments created controversy that continues today. The labeled release experiment produced positive results that matched pre-mission criteria for detecting life. Soil samples released radioactive carbon dioxide when exposed to nutrients, and this activity was eliminated when samples were heated to sterilizing temperatures, exactly as expected if microorganisms were present. However, the other experiments produced ambiguous or negative results, and most scientists concluded that unusual soil chemistry, rather than biology, explained the observations. Gilbert Levin, principal investigator for the labeled release experiment, maintained throughout his life that Viking detected Martian microorganisms. His arguments gained renewed attention as subsequent missions revealed that Mars was more habitable than previously thought, with evidence of past water, organic molecules, and potentially habitable environments. The Viking results remind us how difficult it is to recognize life when we encounter it in unfamiliar forms or environments, a challenge that will only grow as we explore more exotic worlds. While Viking searched for life directly, the Voyager missions took a different approach, carrying messages from Earth to any alien civilizations that might someday encounter these spacecraft. Voyager 1 and Voyager 2, launched in 1977, each carried a golden record containing sounds and images from Earth, a cosmic message in a bottle cast into the interstellar ocean. The golden records, developed under Carl Sagan's direction, represent humanity's attempt to introduce ourselves to unknown cosmic neighbors. Each 12-inch gold-plated copper disc contains 115 images encoded in analog form, showing Earth's landscapes, human anatomy, scientific diagrams, and cultural activities. The audio portion includes greetings in 55 languages, from ancient Akkadian to modern Wu Chinese, representing humanity's linguistic diversity. Natural sounds like thunder, wind, and animal calls paint an acoustic portrait of Earth's biosphere. The musical selections on the golden records reveal the challenge of representing human culture to alien minds. The committee chose pieces ranging from Bach's Brandenburg Concerto to Chuck Berry's Johnny B. Good, from Azerbaijani bagpipes to Peruvian panpipes. These selections attempted to showcase human creativity while acknowledging the impossibility of fully representing our species' artistic achievements in 90 minutes of audio. The inclusion of brain waves from Andrew Yen, who later married Carl Sagan, adds an intimate human element to this cosmic communication. Instructions for playing the records, etched on their covers in symbolic language, represent an attempt at universal communication. The diagrams show how to construct a playback device, using the spin-flip transition of hydrogen atoms as a universal time unit. Whether alien beings could decipher these instructions remains unknown, but the effort represents humanity's optimistic assumption that intelligence anywhere would share certain logical and mathematical foundations. The Pioneer plaques, attached to Pioneer 10 and 11 launched in the early 1970s, preceded the Voyager records as humanity's first deliberate messages to the cosmos. These 6 by 9-inch gold anodized aluminum plates carry simpler messages than the Voyager records but introduced several symbolic conventions for cosmic communication. The famous illustration of nude human figures sparked controversy about representation and censorship, while the pulsar map showing Earth's location raised concerns about revealing our position to potentially hostile civilizations. Beyond their role as interstellar messages, these missions revolutionized our understanding of the outer solar system's potential for harboring life. Voyager's observations of Jupiter's moon Europa revealed a fractured ice surface suggesting a subsurface ocean, instantly making this moon one of the most promising locations for extraterrestrial life. The discovery that tidal heating from Jupiter's gravity could maintain liquid water far from the Sun's warmth expanded concepts of habitability beyond traditional habitable zones. Saturn's moon Titan, shrouded in a thick atmosphere, proved even more intriguing than expected. Voyager 1's flyby revealed an atmosphere denser than Earth's, composed primarily of nitrogen with methane and other organic compounds. This discovery suggested that Titan might host complex chemistry similar to early Earth, though at much colder temperatures. The possibility of exotic forms of life using liquid methane instead of water as a solvent expanded our concepts of biochemistry. Enceladus, another of Saturn's moons, emerged as an unexpected astrobiological target when Voyager detected its unusually bright, geologically young surface. Later missions would reveal geysers erupting from its south pole, spraying water and organic compounds into space from a subsurface ocean. This discovery placed Enceladus alongside Europa as a prime target for astrobiological exploration, demonstrating that habitable environments might be common in the outer solar system. The Galileo mission to Jupiter, operating from 1995 to 2003, provided detailed observations that strengthened the case for Europa's subsurface ocean. Magnetometer measurements revealed that Europa has an induced magnetic field, best explained by a global layer of electrically conductive fluid beneath its ice shell. Images showed a surface dominated by ridges, cracks, and regions of disrupted terrain suggesting active geological processes driven by tidal heating. Galileo also discovered that Ganymede, Jupiter's largest moon, likely harbors a subsurface ocean beneath a thick ice shell. Even Callisto, the most heavily cratered and seemingly dead of Jupiter's large moons, showed evidence of a possible subsurface ocean. These discoveries suggested that liquid water environments might be common throughout the outer solar system, dramatically expanding the number of potentially habitable worlds in our cosmic neighborhood. The Cassini-Huygens mission to Saturn, arriving in 2004, revolutionized our understanding of that system's astrobiological potential. The Huygens probe descended through Titan's atmosphere, revealing a world with methane rain, hydrocarbon lakes, and complex organic chemistry. Images from Titan's surface showed rounded pebbles suggesting fluid erosion, dry riverbeds indicating seasonal methane flows, and vast dune fields shaped by alien winds. Cassini's multiple flybys of Enceladus detected not just water in its geysers but also organic compounds, salts, and silica particles suggesting hydrothermal activity on the ocean floor. These hydrothermal vents, similar to those hosting rich ecosystems in Earth's deep oceans, provide energy in chemical gradients that could support life. The discovery that we could sample Enceladus's ocean by flying through its geysers made this small moon an irresistible target for future astrobiology missions. Mars exploration entered a new era with rovers serving as mobile geological laboratories. Sojourner, the first successful Mars rover in 1997, demonstrated the feasibility of surface mobility. Spirit and Opportunity, landing in 2004, discovered extensive evidence of past water, including minerals that form only in aqueous environments and geological features carved by flowing water. These discoveries transformed Mars from a dry, dead world into a planet with a complex hydrological history. Curiosity, reaching Mars in 2012, carried instruments specifically designed to assess past and present habitability. Its discoveries have been remarkable: ancient streambeds, lakebeds that existed for millions of years, organic molecules preserved in mudstone, and seasonal variations in atmospheric methane that might indicate ongoing biological or geological processes. The detection of organic compounds doesn't prove life existed, but it shows that the chemical building blocks were present. The Perseverance rover, landing in 2021, takes the search for ancient Martian life even further. Landing in Jezero crater, site of an ancient river delta, Perseverance seeks signs of past microbial life preserved in sedimentary rocks. Its sophisticated instruments can detect organic compounds and minerals associated with biological processes. Most ambitiously, Perseverance is collecting and caching samples for eventual return to Earth, where they can be analyzed with instruments too large and complex to send to Mars. The exploration of asteroids and comets has revealed these small body. These discoveries support the concept of panspermia, the hypothesis that life or its precursors can travel between worlds. Meteorites from Mars have been found on Earth, demonstrating that material can transfer between planets. Some of these meteorites contain structures that some researchers interpret as fossilized microorganisms, though this interpretation remains highly controversial. The possibility that life might spread naturally between worlds adds complexity to our search, suggesting that life on different worlds might share common origins. The discovery of life thriving in Earth's most hostile environments has fundamentally transformed our understanding of life's possibilities throughout the universe. These extremophiles, organisms that not only survive but flourish in conditions that would instantly kill most life forms, have shattered preconceptions about the requirements for life and dramatically expanded the range of potentially habitable environments we must consider in our cosmic search. The revolution began in the 1970s with the discovery of thriving ecosystems around deep-sea hydrothermal vents, places where superheated water laden with toxic chemicals erupts from the ocean floor into the crushing darkness of the deep sea. The submersible Alvin, exploring the Galapagos Rift in 1977, revealed dense communities of giant tube worms, ghostly crabs, and peculiar fish living in complete darkness, sustained not by sunlight but by chemical energy from the Earth itself. These vent ecosystems operate on chemosynthesis rather than photosynthesis, with bacteria converting hydrogen sulfide and other chemicals into organic compounds that form the base of the food web. The discovery that life could thrive independently of sunlight suggested that similar ecosystems might exist in the subsurface oceans of Europa or Enceladus, where hydrothermal vents could provide both energy and nutrients for potential life forms. The tube worms at these vents, some growing over 6 feet long, demonstrated that complex multicellular life could evolve in these extreme environments. The bacteria thriving at hydrothermal vents withstand temperatures that would denature most proteins, with some hyperthermophiles growing optimally at temperatures above the boiling point of water at sea level. Paralobus fumarii holds the current record, reproducing at temperatures up to 113 degrees Celsius and surviving brief exposures to 121 degrees Celsius, the temperature used to sterilize medical equipment. These organisms achieve this feat through specialized proteins that remain stable at extreme temperatures and DNA repair mechanisms that quickly fix heat-induced damage. In the opposite extreme, psychrophiles thrive in permanently frozen environments that would seem utterly inhospitable to life. Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, harbors diverse microbial communities that have been isolated from the surface for potentially millions of years. These organisms survive in liquid water that remains unfrozen due to pressure and geothermal heat, conditions similar to what might exist beneath the ice shells of outer solar system moons. Arctic permafrost contains bacteria that remain metabolically active at temperatures as low as -20 degrees Celsius, slowly repairing DNA damage and maintaining cellular functions in a state of extreme slow motion. Some bacteria recovered from ancient permafrost have been successfully revived after being frozen for millions of years, suggesting that life could persist in dormant states through cosmic timescales, potentially surviving interplanetary or even interstellar journeys. The discovery of organisms living within solid rock kilometers beneath Earth's surface revealed a vast deep biosphere that might contain more biomass than all surface life combined. These endoliths, living in microscopic spaces within rock, survive on hydrogen produced by radioactive decay splitting water molecules, existing entirely independently of solar energy. Some deep subsurface bacteria divide only once per century or millennium, operating on timescales that challenge our conception of life as a dynamic process. These deep biosphere discoveries suggest that rocky planets and moons might harbor life far beneath their surfaces, protected from radiation and temperature extremes that would sterilize their surfaces. Mars, with its thin atmosphere and lack of magnetic field, has a hostile surface environment, but life might persist kilometers underground where liquid water could exist and rocks provide protection from cosmic radiation. The same principle applies to asteroids and comets, which might harbor protected niches for life in their interiors. Halophiles thrive in environments saturated with salt, conditions that would fatally dehydrate most organisms. The Dead Sea, despite its name, hosts diverse microbial communities, while even more extreme halophiles live in salt evaporation ponds where salt concentrations approach saturation. These organisms have evolved sophisticated mechanisms to balance osmotic pressure, some accumulating compatible solutes internally while others use specialized ion pumps to maintain appropriate salt concentrations. The discovery of halophiles has implications for Mars, where perchlorates in the soil create an extremely salty environment. Rather than making Mars uninhabitable, these salts might provide niches for specialized organisms. Recurring slope lineae, dark streaks that appear seasonally on Martian slopes, might represent briny water flows where halophilic organisms could potentially survive. Some researchers suggest that the controversial Viking-labeled release results might be explained by halophilic organisms that Earth-based tests weren't designed to detect. Acidophiles flourish in environments with pH values approaching 0, equivalent to battery acid. The Rio Tinto in Spain, colored blood red by dissolved iron, maintains a pH around 2 and hosts diverse microbial communities that have survived for potentially millions of years. These organisms thrive in conditions that dissolve metal, using specialized proteins that function in extreme acidity and cell membranes that prevent hydrogen ions from flooding into the cell. Alkalophiles occupy the opposite extreme, living in environments with pH values above 11, similar to household ammonia. Mono Lake in California and Soda Lakes in Africa's Rift Valley host complex ecosystems based on alkalophilic bacteria. These discoveries suggest that life could exist across an enormous range of chemical conditions, greatly expanding the types of alien environments we should consider potentially habitable. Radiotrophs represent one of the most remarkable extremophile discoveries, organisms that use radiation as an energy source. Fungi growing in the ruins of the Chernobyl nuclear reactor contain melanin that appears to convert gamma radiation into chemical energy, similar to how plants use chlorophyll to capture light energy. These organisms thrive in radiation fields that would cause severe damage to most life forms, suggesting that life might exist in high radiation environments like Jupiter's moon Europa, where the radiation environment would quickly kill unprotected Earth organisms. Such organisms could potentially survive in space or on worlds with thin atmospheres that provide little radiation protection. Xerophiles thrive in extremely dry conditions where water activity approaches zero. The Atacama Desert in Chile, one of Earth's driest places with some regions receiving no measurable rainfall for decades, hosts microbial communities that survive on minute amounts of water extracted from rare fog events or deliquescent salts that pull moisture from the air. Some organisms in the Atacama enter cryptobiotic states, essentially shutting down metabolism until water becomes available, then rapidly resuming activity. These desert extremophiles provide models for how life might persist on Mars, where the surface is extremely dry but water ice exists just below the surface in many regions. Morning frost observed by Mars landers and seasonal dark flows on crater walls suggest that liquid water, however briefly, might occasionally be available. Xerophilic organisms could potentially exploit these transient water sources, surviving long dry periods in dormant states. Barophiles, also called piezophile, thrive under extreme pressure in the deep ocean trenches. Some species require pressures hundreds of times greater than at sea level and cannot survive when brought to the surface. These organisms have evolved proteins that function only under high pressure and cell membranes that remain fluid despite compression that would solidify normal membranes. The discovery of barophiles suggests that life could exist in the high-pressure environments of giant planet atmospheres or the deep oceans of large moons. Polyextremophiles survive multiple extreme conditions simultaneously, demonstrating life's remarkable adaptability. Some organisms near deep-sea vents tolerate high temperature, high pressure, extreme pH, and toxic chemical concentrations simultaneously. The Archean Picrophilus torridus thrives at pH 0 and temperatures up to 65 degrees Celsius, conditions that would separately kill most organisms and seem impossibly hostile in combination. These polyextremophiles suggest that alien life might exist in environments with multiple extremes that we haven't yet imagined. Venus's upper atmosphere, with its sulfuric acid clouds, intense UV radiation, and extreme temperatures at lower altitudes, might seem completely hostile, yet some researchers propose that polyextremophilic organisms could potentially survive in temperate cloud layers, using sulfur compounds for energy and staying aloft through biological processes. The study of extremophiles has revealed that life uses diverse energy sources beyond sunlight and organic compounds. Some organisms derive energy from iron oxidation, sulfur reduction, methane production, or even electricity from rocks. This metabolic diversity suggests that alien life might use energy sources we haven't considered, potentially thriving in environments that seem energetically barren from our Earth-centric perspective. Tardigrades, microscopic animals also known as water bears, represent the ultimate extremophiles, surviving conditions that kill even the hardiest bacteria. These remarkable creatures can withstand temperatures from near absolute zero to over 150 degrees Celsius, pressures from vacuum to 6,000 atmospheres, and radiation doses thousands of times the lethal dose for humans. Tardigrades achieve this by entering cryptobiosis, replacing water in their cells with protective sugars and essentially pausing their metabolism until conditions improve. Experiments have shown that tardigrades can survive exposure to open space, enduring vacuum, cosmic radiation, and temperature extremes simultaneously. Some researchers suggest that organisms like tardigrades could potentially survive interplanetary transfer on meteorites, supporting the panspermia hypothesis. If Earth life can survive space exposure, it becomes more plausible that life could spread naturally between worlds, complicating our search for truly independent genesis of life. The confirmation of planets orbiting other stars transformed the search for extraterrestrial life from speculation about possibilities into investigation of actual worlds. This exoplanet revolution, beginning in the 1990s and accelerating dramatically with space-based telescopes, has revealed a cosmos filled with planetary systems far more diverse and numerous than astronomers had dared imagine, each discovery reshaping our understanding of planet formation and the potential for life throughout the universe. The first confirmed detection of an exoplanet orbiting a main sequence star came in 1995 when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a gas giant planet orbiting its star every 4.2 days. This discovery shattered expectations, as the planet's proximity to its star placed it well inside where Mercury orbits our Sun, in a region where planetary formation theory suggested no planets should exist. This hot Jupiter forced astronomers to reconsider their models of planetary system formation and migration. The radial velocity method used to detect 51 Pegasi b relies on the gravitational dance between star and planet. As a planet orbits its star, both bodies actually orbit their common center of mass. For a massive planet orbiting close to its star, this causes the star to wobble measurably, moving toward and away from Earth with a regular period. This motion creates a Doppler shift in the star's light, with spectral lines shifting toward blue when the star approaches and toward red when it recedes. By measuring these minute shifts, astronomers can determine the planet's minimum mass and orbital period. Following this breakthrough, discoveries accumulated rapidly as astronomers refined their techniques and dedicated more telescope time to planet hunting. Each new discovery revealed unexpected diversity: planets orbiting binary stars like Tatooine from Star Wars, planets with wildly eccentric orbits carrying them from scorching proximity to their stars out to freezing distances, and planetary systems packed with multiple worlds and resonant chains where gravitational interactions create cosmic harmonies. The transit method revolutionized exoplanet detection by enabling the discovery of smaller planets and providing additional information about planetary properties. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light, creating a characteristic dimming that repeats with each orbit. The depth of this dimming reveals the planet's size relative to its star, while the duration indicates the orbital distance. Combined with radial velocity measurements, transits allow astronomers to determine a planet's density, providing clues about its composition. Ground-based transit surveys like HAT, WASP, and KELT discovered numerous hot Jupiters, but detecting Earth-sized planets required escaping Earth's turbulent atmosphere. The French space telescope Corot, launched in 2006, pioneered space-based transit detection, discovering dozens of planets including the first confirmed rocky exoplanet. These early successes set the stage for a mission that would transform our understanding of planetary populations throughout the galaxy. NASA's Kepler Space Telescope, launched in 2009, stared continuously at over 150,000 stars in a single patch of sky, monitoring their brightness with extraordinary precision. This unwavering gaze allowed Kepler to detect the minute dimming caused by Earth-sized planets transiting sun-like stars, measurements impossible from Earth's surface. Over its primary mission and extended K2 mission, Kepler discovered over 2,500 confirmed planets and thousands more candidates awaiting confirmation. Kepler's discoveries revealed that planets are the rule rather than the exception, with most stars hosting at least one planet. Small planets proved far more common than gas giants, with super-Earths and mini-Neptunes, planet types absent from our solar system, dominating the population. These intermediate-sized worlds, larger than Earth but smaller than Neptune, challenged formation theories and suggested that our solar system's architecture might be unusual rather than typical. The discovery of Kepler-452b in 2015 captured public imagination as Earth's cousin, a planet only 60% larger than Earth orbiting within its star's habitable zone. Though its star is slightly larger and older than our Sun, the planet receives similar stellar energy to Earth, making it a prime candidate for hosting liquid water and potentially life. This discovery demonstrated that potentially habitable worlds orbit other stars, transforming the search for life from hopeful speculation to targeted investigation of specific worlds. Kepler revealed numerous multi-planet systems, some containing 6 or more confirmed planets. The Kepler-11 system amazed astronomers with 6 planets orbiting closer to their star than Venus orbits our Sun, their density suggesting thick atmospheres or even global oceans. TRAPPIST-1, discovered by ground-based telescopes and characterized by Kepler's K2 mission, hosts 7 Earth-sized planets, 3 within the habitable zone, orbiting an ultra-cool dwarf star just 39 light-years from Earth. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, expanded the search to the entire sky, focusing on bright, nearby stars where follow-up observations are most feasible. TESS has discovered planets orbiting some of the nearest stars to Earth, worlds that future telescopes will study in detail. Its discoveries include TOI 700d, an Earth-sized planet in its star's habitable zone just 100 light-years away, close enough for detailed atmospheric studies with next-generation telescopes. Direct imaging of exoplanets, though challenging due to the overwhelming brightness of stars compared to planets, has revealed young, massive planets orbiting far from their stars. These observations provide unique information about planetary atmospheres and compositions impossible to obtain through indirect methods. The 4 planets orbiting HR 8799, captured in a stunning time-lapse showing their orbital motion over 7 years, demonstrated that we can now watch alien solar systems evolve in real time. Gravitational microlensing, where a planet's gravity briefly magnifies light from a background star, has revealed planets invisible to other techniques, including free-floating planets wandering through interstellar space without parent stars. These rogue planets, potentially numbering in the billions in our galaxy alone, challenge our understanding of planet formation and raise intriguing possibilities for life in unexpected places, perhaps warmed by radioactive decay or thick hydrogen atmospheres rather than stellar radiation. The discovery of planets orbiting red dwarf stars has particular significance for the search for life. These small, cool stars comprise 75% of all stars and remain stable for trillions of years, providing immense timescales for biological evolution. Proxima Centauri b, orbiting the nearest star to our Sun, lies within its star's habitable zone despite orbiting just 7 million kilometers from the star. The TRAPPIST-1 system demonstrates that red dwarfs can host multiple potentially habitable worlds, dramatically increasing the number of environments where life might exist. However, red dwarf planets face unique challenges. These stars are prone to powerful flares that could strip atmospheres from nearby planets. Planets in the habitable zones of red dwarfs are likely tidally locked, with one hemisphere in permanent daylight and the other in eternal darkness. Yet climate models suggest that atmospheres could transport heat from day to night sides, maintaining habitable conditions in twilight zones or even globally if atmospheric circulation is efficient. The discovery of planets orbiting ancient stars in our galaxy's thick disk and halo populations has temporal implications for life's emergence. Some of these stars formed over 10 billion years ago, when the universe contained fewer heavy elements necessary for rocky planet formation. Yet planets exist around these ancient stars, suggesting that potentially habitable worlds have existed for most of cosmic history, providing vast timescales for life to evolve and potentially develop intelligence long before Earth formed. Statistical analysis of Kepler data suggests that 20 to 50% of Sun-like stars host Earth-sized planets within their habitable zones. Extrapolating to the entire galaxy implies billions of potentially habitable worlds in the Milky Way alone. This stunning abundance makes the Fermi Paradox even more puzzling. With so many potential homes for life, why does the universe appear empty of obvious signs of intelligence? The characterization of exoplanet atmospheres through spectroscopy has begun revealing their compositions, a crucial step toward detecting biosignatures. When planets transit their stars, stellar light filters through their atmospheres, imprinting absorption features from atmospheric gases. The Hubble and Spitzer space telescopes have detected water vapor, methane, carbon dioxide, and even clouds and hazes in exoplanet atmospheres, demonstrating that we can study alien atmospheres from light-years away. The James Webb Space Telescope, launched in 2021, has revolutionized exoplanet atmosphere studies with its unprecedented infrared sensitivity and spectroscopic capabilities. This magnificent observatory, positioned at the second Lagrange point 1.5 million kilometers from Earth, can detect and analyze the faint signals from exoplanet atmospheres with precision impossible for previous telescopes. Its observations are revealing atmospheric compositions, temperature structures, and even weather patterns on worlds light-years away, bringing us closer to identifying potentially habitable environments and possible biosignatures. Webb's early observations have exceeded expectations, detecting water vapor, methane, carbon dioxide, and other molecules in exoplanet atmospheres with remarkable clarity. The telescope's ability to observe in infrared wavelengths is particularly crucial, as many important molecules have their strongest absorption features in this part of the spectrum. Water vapor, methane, and carbon dioxide, all relevant to habitability and potential biosignatures, are most easily detected in the infrared, making Webb ideally suited for astrobiological investigations. The K2-18b observations represent a milestone in the search for potentially habitable worlds. This subneptune, 8 times Earth's mass and located 120 light-years away, shows evidence of water vapor and possibly dimethyl sulfide in its atmosphere, a molecule that on Earth is primarily produced by marine phytoplankton. While the detection remains tentative and the planet's large size makes it unlikely to be truly Earth-like, these observations demonstrate our growing ability to detect molecules potentially associated with biological processes. The diversity of exoplanets discovered has forced us to reconsider what makes a world habitable. Super-Earths, planets larger than Earth but smaller than Neptune, might maintain thick hydrogen atmospheres that create greenhouse effects sufficient to warm planets far outside traditional habitable zones. Water worlds, planets covered entirely by deep oceans, might host life in their vast seas despite lacking the land-based weathering cycles that regulate Earth's climate. Desert planets with limited water might concentrate life in specific regions while remaining globally habitable. The concept of the habitable zone itself has evolved from a simple temperature-based definition to a complex consideration of atmospheric composition, stellar evolution, and planetary dynamics. The inner edge depends on when a runaway greenhouse effect would evaporate oceans, while the outer edge depends on the maximum greenhouse effect possible before carbon dioxide clouds increase planetary albedo. These boundaries shift based on planetary mass, atmospheric composition, and stellar characteristics, making the habitable zone a fuzzy region rather than sharp boundaries. Planetary migration, revealed by the unexpected locations of many exoplanets, suggests that worlds might move into or out of habitable zones over time. Hot Jupiters likely formed in outer regions of their systems before migrating inward, potentially disrupting terrestrial planets along the way. Conversely, planets might migrate outward as their stars evolve, spending different epochs of their history in the habitable zone. This migration adds a temporal dimension to habitability, suggesting that life might arise during specific windows of opportunity. The discovery of circumbinary planets, worlds orbiting 2 stars simultaneously, expands potential habitable environments. These planets experience complex but predictable variations in stellar heating as their 2 suns orbit each other. Models suggest that some circumbinary planets could maintain stable climates despite these variations, potentially hosting life under double sunrises and sunsets that would create spectacular and ever-changing sky displays. The search for evidence of life beyond Earth has evolved into 2 complementary approaches: detecting biosignatures that indicate biological processes and identifying technosignatures that would reveal technological civilizations. These twin strategies require different observational techniques, face distinct challenges, and carry unique implications for understanding life's prevalence and nature throughout the cosmos. As our instruments become more sensitive and our understanding of life's possibilities expands, we're developing increasingly sophisticated methods to recognize the subtle signs that might betray the presence of life across interstellar distances. Biosignatures represent any observable phenomenon that indicates the presence of life, from atmospheric gases maintained out of chemical equilibrium to surface features modified by biological processes. The most compelling biosignatures are those that cannot be easily explained by non-biological processes, though distinguishing biological from geological or photochemical origins remains one of astrobiology's greatest challenges. Earth's atmosphere provides our template for understanding biosignatures, though we must remain open to possibilities beyond our terrestrial experience. Oxygen represents the most discussed potential biosignature, comprising 21% of Earth's atmosphere due to photosynthesis by plants, algae, and cyanobacteria. Without continuous biological production, oxygen would disappear from Earth's atmosphere within a few million years, consumed by oxidation of surface rocks and organic matter. The presence of abundant oxygen in an exoplanet's atmosphere would suggest active biological production, though we must consider non-biological sources like photolysis of water vapor followed by hydrogen escape. The simultaneous presence of oxygen and methane creates an even stronger biosignature than either gas alone. These gases react rapidly in the presence of sunlight, so their coexistence requires continuous replenishment. On Earth, methane is produced primarily by methanogenic archaea in anaerobic environments and by human agricultural activities. The combination of oxygen from photosynthesis and methane from anaerobic metabolism would strongly suggest a living world with diverse metabolisms operating in different environmental niches. Phosphine has gained attention as a potential biosignature after its controversial detection in Venus's atmosphere. On Earth, phosphine is produced almost exclusively by anaerobic bacteria or industrial processes, making it a promising biosignature for life that doesn't rely on oxygen. The reported detection of phosphine in Venus's cloud sparked intense debate about possible aerial life in the planet's temperate cloud layers, though subsequent observations have questioned the initial detection, illustrating the challenges of biosignature confirmation. The vegetation red edge represents a surface biosignature detectable through spectroscopy. Plants absorb visible light for photosynthesis but strongly reflect near-infrared radiation to avoid overheating. This creates a sharp increase in reflectance around 750 nanometers wavelength, visible as a distinctive spectral feature. Detecting such features on exoplanets would suggest photosynthetic organisms covering substantial surface areas, though we must consider that alien photosynthesis might operate at different wavelengths depending on the star's spectrum. Seasonal variations in atmospheric composition or surface features could indicate biological activity responding to changing environmental conditions. Earth's atmospheric carbon dioxide shows annual cycles as plants grow during summer and decay during winter. Methane concentrations vary seasonally due to wetland activity and agricultural cycles. Detecting similar patterns on exoplanets would suggest dynamic biological processes, though distinguishing biological from geological seasonality requires careful analysis. Disequilibrium chemistry provides a more general biosignature than specific gases. Living systems maintain chemical disequilibrium by constantly processing energy and materials, creating compositions that wouldn't exist in a lifeless environment. Earth's atmosphere, with its mixture of oxidizing and reducing gases, represents extreme disequilibrium maintained by the global biosphere. Identifying similar disequilibrium in exoplanet atmospheres would suggest active processes, possibly biological, preventing chemical equilibrium. However, false positives complicate biosignature interpretation. Oxygen can be produced abiotically through photolysis of water vapor, particularly around stars with high ultraviolet output. Runaway greenhouse atmospheres might generate oxygen as water vapor rises to altitudes where ultraviolet light splits molecules, with lightweight hydrogen escaping to space. Distinguishing biological from non-biological oxygen requires understanding the planet's overall context, including stellar radiation, atmospheric composition, and surface conditions. Technosignatures, evidence of technology using civilizations, offer more definitive proof of intelligence but might be far rarer than biosignatures. These signatures range from electromagnetic emissions to megascale engineering projects, each requiring different search strategies and facing unique detection challenges. The search for technosignatures assumes that alien civilizations would modify their environments in detectable ways, either intentionally or as unavoidable consequences of their technology. Radio and optical communications remain the most actively searched technosignatures. Narrowband radio signals, concentrated at specific frequencies rather than spread across the spectrum, strongly suggest artificial origin since natural astrophysical processes produce broadband emission. Pulsed signals with mathematical patterns, repeating sequences, or encoded information would provide even stronger evidence of intelligence. Optical SETI searches for powerful laser pulses that might be used for interstellar communication or propulsion. Industrial pollutants in exoplanet atmospheres could reveal technological civilizations. Chlorofluorocarbons, CFCs, entirely artificial on Earth, would persist in atmospheres for thousands of years and could be detected spectroscopically. Nitrogen dioxide from combustion, sulfur hexafluoride from electrical equipment, or other industrial gases might indicate technological activity. The detection of short-lived artificial molecules would suggest ongoing industrial processes, providing evidence of active technology use. Megastructures represent the most dramatic technosignatures, massive engineering projects visible across interstellar distances. A Dyson sphere or swarm, collecting a significant fraction of a star's energy output, would be invisible in optical light but bright in infrared as it re-radiated waste heat. Stellar engines, using stellar radiation pressure or magnetic fields to move entire star systems, would create unusual proper motions detectable through precise astrometry. Ring worlds, shell worlds, or other massive constructs might create distinctive transit signatures unlike natural planets. The search for Dyson spheres has examined thousands of stars looking for unusual infrared excesses that might indicate energy harvesting structures. While several candidates have been identified, including Boyajian star with its mysterious dimming episodes, all have plausible natural explanations. The absence of obvious Dyson spheres around nearby stars suggests that either advanced civilizations are rare or they don't build such structures, perhaps finding more efficient energy sources or choosing not to expand their energy consumption indefinitely. Atmospheric or surface modifications for terraforming might create detectable technosignatures. A civilization attempting to warm a cold planet might release powerful greenhouse gases, while cooling a hot planet might require atmospheric aerosols or orbital mirrors. Large-scale albedo modifications, perhaps darkening polar ice to increase heating or brightening surfaces to increase cooling, could be visible through photometric monitoring. These planetary engineering projects would create signatures distinct from natural climate variations. Waste heat represents an unavoidable technosignature of energy-using civilizations. The laws of thermodynamics require that all energy use eventually produces waste heat, radiated as infrared emission. A civilization using large amounts of energy would warm their planet above equilibrium temperature, potentially detectable through precise infrared observations. Galaxy-spanning civilizations might warm entire galaxies, creating infrared excesses visible across cosmic distances. Artificial illumination of planetary night sides could reveal technological civilizations. Earth's night side glows with city lights, visible from space and potentially detectable on nearby exoplanets with future telescopes. The spectrum of artificial lighting differs from natural sources, with LED lights producing distinctive spectral features. Regular patterns in illumination, perhaps following transportation networks or population centers, would strongly suggest intelligent origin. Propulsion signatures from interstellar spacecraft might be detectable, particularly if civilizations use fusion rockets, antimatter drives, or other high-energy propulsion systems. The exhaust from such drives could create distinctive spectral signatures or gamma-ray emissions. Light sails accelerated by powerful lasers might create brief, intense flashes detectable across interstellar distances. Even chemical rockets might be detectable during massive launch campaigns if civilizations attempt interstellar colonization. Communication leakage, the unintended emission of electromagnetic signals into space, might reveal civilizations similar to our own. Earth has been broadcasting radio and television signals for roughly a century, creating an expanding sphere of detectable emissions now over 200 light-years in diameter. However, our emissions are weakening as communication technology becomes more efficient, suggesting a brief window of detectability that might apply to other civilizations. The temporal aspect of technosignatures presents unique challenges. Civilizations might use detectable technology only briefly before moving to more efficient or less detectable methods. The synchronicity problem becomes acute for technosignatures, requiring not just simultaneous existence but compatible technological development. A civilization that transmitted powerful signals a million years ago or will develop technology a million years hence remains invisible to our current searches. Artifact SETI searches for physical objects that alien civilizations might have left in our solar system. These could include probes monitoring Earth, monuments or messages for emerging civilizations, or mining equipment extracting resources from asteroids. The solar system's Lagrange points, gravitationally stable locations where objects can remain with minimal energy expenditure, represent logical places to search for alien artifacts. The contemporary search for extraterrestrial intelligence has evolved into a sophisticated, multifaceted endeavor employing cutting-edge technology, innovative search strategies, and unprecedented computational power. Modern programs have moved beyond the simple radio searches of earlier decades, incorporating optical observations, advanced signal processing, machine learning algorithms, and coordinated global efforts that transform the entire Earth into a detection instrument for alien signals. Breakthrough Listen, launched in 2015 with a $100 million commitment from entrepreneur Yuri Milner, represents the most comprehensive SETI program ever undertaken. This ambitious project observes millions of stars across multiple wavelengths, employs the world's most powerful radio telescopes, and generates more data in a single day than earlier SETI projects collected in entire years. The program's open-source approach, making all data publicly available, has democratized the search for extraterrestrial intelligence and enabled independent research. The program utilizes the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world, capable of observing frequencies from 100 MHz to 100 GHz with extraordinary sensitivity. The Parkes Radio Telescope in Australia provides Southern Hemisphere coverage, ensuring that no part of the sky remains unobserved. The automated planet finder at Lick Observatory conducts optical searches for laser pulses, while the Meerkat Array in South Africa adds interferometric capabilities that can observe multiple star systems simultaneously. Breakthrough Listen's target selection strategy prioritizes nearby stars, particularly those known to host potentially habitable planets. The program observes the nearest million stars, the centers of the 100 nearest galaxies, and the galactic plane, covering an unprecedented volume of space. Special attention focuses on stars with confirmed exoplanets in habitable zones, anomalous stars like Boyajian star that show unusual behavior, and locations where interstellar visitors like Oumuamua originated. The data processing challenges are staggering, with each observation generating terabytes of data that must be analyzed for potential signals. Machine learning algorithms trained on known interference patterns help identify and remove terrestrial contamination, while other algorithms search for patterns that might indicate artificial origin. The program has developed new techniques for detecting signals that drift in frequency due to relative motion between transmitter and receiver, a signature that would strongly suggest an extraterrestrial origin. The Chinese 500-meter aperture spherical telescope, FAST, the world's largest single-dish radio telescope, has joined the search with unique capabilities. Its enormous collecting area provides unprecedented sensitivity, potentially detecting signals too weak for other telescopes. FAST's 19-beam receiver can observe multiple positions simultaneously, accelerating sky surveys. Chinese researchers have developed their own SETI programs, including searches for signals from nearby star systems and observations of repeating fast radio bursts that, while likely natural, demonstrate the telescope's ability to detect brief, powerful signals from cosmic distances. The Square Kilometre Array, SKA, currently under construction in Australia and South Africa, will revolutionize SETI capabilities when fully operational. This massive interferometer will combine signals from thousands of individual antennas spread across thousands of kilometers, creating unprecedented sensitivity and resolution. The SKA will be capable of detecting airport radar systems at distances of dozens of light-years, television broadcasts from hundreds of light-years, and directed transmissions from across the galaxy. The SKA's SETI programs will conduct commensal observations, searching for artificial signals while the telescope performs other astronomical observations. This approach maximizes observing efficiency, allowing SETI searches to piggyback on studies of pulsars, galaxies, and cosmic hydrogen. The telescope's wide field of view will enable surveys of millions of stars simultaneously, potentially detecting signals that narrower searches might miss. Optical SETI has matured into a major component of modern searches, with dedicated telescopes scanning for nanosecond laser pulses that might indicate interstellar communication. The Veritas Gamma-Ray Telescope Array has demonstrated that atmospheric Cherenkov telescopes, designed to detect cosmic gamma rays, can also search for optical pulses with nanosecond time resolution. These facilities can detect laser pulses that briefly outshine entire stars, signals that advanced civilizations might use for communication or propulsion. The Laser SETI project takes a different approach, using multiple small telescopes to continuously monitor the entire sky for laser pulses. Unlike traditional telescopes that observe specific targets, Laser SETI watches everywhere simultaneously, ensuring that transient signals aren't missed because telescopes were pointing elsewhere. This all-sky approach is particularly important for detecting signals from civilizations that might not be targeting Earth specifically. The search for fast radio bursts, FRBs, has unexpectedly contributed to SETI research. These millisecond duration radio pulses, first discovered in 2007, release enormous amounts of energy and originate from distant galaxies. While FRBs are almost certainly natural phenomena, possibly from magnetars or other exotic objects, their study has developed techniques directly applicable to SETI. The discovery that some FRBs repeat has enabled detailed studies of their properties, demonstrating our ability to detect and characterize brief signals from cosmic distances. SETI Institute's Allen Telescope Array continues expanding, with plans for hundreds of antennas that will work together as a dedicated SETI instrument. Unlike large telescopes that must divide time between multiple research programs, the ATA focuses primarily on SETI observations, enabling long-duration monitoring of interesting targets. The array's ability to observe multiple star systems simultaneously accelerates surveys while maintaining sensitivity to weak signals. The Galileo project, established in 2021, takes an unconventional approach by searching for evidence of extraterrestrial technology within our solar system. Led by astronomer Avi Loeb, the project develops networks of telescopes to monitor the sky for unusual objects that might represent alien probes or artifacts. This approach acknowledges that advanced civilizations might explore the galaxy using robotic probes rather than electromagnetic signals, and that such probes might occasionally visit our solar system. Future missions specifically designed for biosignature detection are in development, promising to revolutionize our ability to identify living worlds. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a census of exoplanets using gravitational microlensing and direct imaging. Its coronagraph instrument will block starlight to directly observe planets, potentially detecting biosignatures in their reflected light. The proposed Habitable Worlds Observatory would be specifically designed to search for biosignatures on Earth-like planets around Sun-like stars. This ambitious mission would use a large segmented mirror and advanced coronagraph to suppress starlight by factors of billions, revealing dim planets and analyzing their atmospheres for signs of life. The telescope would observe dozens of potentially habitable worlds, providing our first statistical understanding of how common living planets might be. The European Space Agency's Plato mission, launching in 2026, will discover and characterize thousands of exoplanets, with particular focus on Earth-like planets in habitable zones. By monitoring bright stars where follow-up observations are feasible, Plato will identify the best targets for atmospheric studies with JWST and future telescopes. The mission's long-duration observations will detect planets with longer orbital periods, including true Earth analogues that current surveys miss. Ground-based telescopes continue advancing with adaptive optics systems that correct for atmospheric turbulence, achieving near-space quality observations from Earth's surface. The extremely large telescopes currently under construction, with mirrors 30 to 40 meters in diameter, will have the resolution to directly image nearby exoplanets and potentially detect biosignatures in their atmospheres. These massive instruments will complement space telescopes, providing different wavelength coverage and observational capabilities. Breakthrough Starshot, another breakthrough initiative project, aims to develop technology for sending tiny probes to nearby star systems within this century. These gram-scale spacecraft, accelerated to 20% light speed by powerful laser arrays, could reach Proxima Centauri in roughly 20 years, returning close-up images and measurements of potentially habitable planets. While primarily a technology development program, Starshot could ultimately provide direct reconnaissance of nearby exoplanets, potentially confirming biosignatures detected by telescopes. The development of quantum sensors promises revolutionary improvements in detection sensitivity. Quantum correlations can reduce noise below classical limits, potentially enabling detection of signals too weak for conventional receivers. Quantum computers might identify patterns in SETI data that classical computers cannot efficiently process, potentially recognizing forms of communication we haven't imagined. Artificial intelligence and machine learning are transforming signal analysis, identifying patterns humans might miss and accelerating data processing by orders of magnitude. Neural networks trained on millions of examples of terrestrial interference can rapidly identify and remove contamination from observations. Unsupervised learning algorithms search for anomalies without preconceived notions of what alien signals might look like, potentially detecting forms of communication beyond human imagination. The concept of the Great Filter emerged from humanity's attempt to reconcile the apparent contradiction between the vast number of potentially habitable worlds and the complete absence of detected alien civilizations. This philosophical framework, developed by economist Robin Hanson in the late 1990s, suggests that somewhere along the path from non-living chemistry to galaxy-spanning civilizations lies an almost insurmountable obstacle that prevents the universe from teeming with intelligent life. Understanding where this filter lies has profound implications not just for our search for cosmic companions, but for humanity's own future survival and expansion into the cosmos. The Great Filter represents one or more evolutionary steps that are extraordinarily improbable, acting as a bottleneck that few or no species successfully navigate. If such a filter exists, it must be powerful enough to prevent the emergence of detectable civilizations despite billions of potentially habitable planets and billions of years of cosmic evolution. The crucial question for humanity is whether we have already passed through this filter, making us extraordinarily rare and fortunate, or whether the filter lies ahead, suggesting a dire future for our species. If the Great Filter lies in our past, several candidates emerge from Earth's history. The origin of life itself might be the filter, requiring such an improbable combination of conditions that Earth represents one of the only worlds where this transition occurred. Despite favorable conditions and rapid geological timescales, life arose only once on Earth as far as we know, with all organisms sharing common biochemistry and genetic machinery. Laboratory attempts to create life from non-living components have failed despite decades of effort, suggesting that abiogenesis might be far more difficult than early experiments suggested. The evolution of prokaryotic to eukaryotic cells represents another potential filter. This transition, involving the incorporation of one cell type within another to create mitochondria and chloroplasts, took nearly 2 billion years on Earth and might have occurred only once. The complexity jump from bacteria to cells with nuclei, internal membranes, and specialized organelles was enormous, enabling the energy metabolism necessary for complex multicellular life. Without this endosymbiotic event, Earth might have remained a world of bacterial mats forever. The development of complex multicellularity could be the filter. Single-celled life dominated Earth for over 3 billion years before complex animals appeared in the Cambrian explosion. The coordination required for cells to specialize, communicate, and sacrifice individual reproduction for the organism's benefit represents a major evolutionary hurdle. While simple multicellularity evolved multiple times, complex differentiated organisms with specialized tissues and organs might be extraordinarily rare. The evolution of intelligence capable of creating technology might be the critical bottleneck. Earth has hosted complex life for over 500 million years, yet technological intelligence emerged only once, very recently in geological terms. The specific combination of factors leading to human intelligence, including social cooperation, language, tool use, and cultural transmission of knowledge, might be highly improbable. The extinction of other hominin species suggests that even approaching human-level intelligence doesn't guarantee survival. If the great filter lies in our future, the implications are sobering. Perhaps civilizations invariably destroy themselves shortly after developing advanced technology. Nuclear weapons, engineered pathogens, artificial intelligence, nanotechnology, or environmental destruction might represent unavoidable extinction risks that no species successfully navigates. The fact that humanity has already faced several close calls with nuclear war suggests that self-destruction might be a common fate for technological species. Climate change and environmental degradation could represent a universal filter. Perhaps all civilizations face a period where their technology damages their planet's life support systems faster than they develop sustainable alternatives. The narrow window between developing industrial technology and either achieving sustainability or causing irreversible damage might be impossible to navigate. Earth's current climate crisis could be a test case for whether technological species can successfully manage planetary-scale challenges. The development of artificial general intelligence might be a universal extinction risk. Perhaps all biological civilizations create artificial intelligence that either replaces them or causes their extinction through misaligned goals or unintended consequences. The rapid advancement of AI technology, combined with the difficulty of ensuring AI systems remain beneficial as they become more powerful, suggests this could be a common failure mode for technological species. Resource depletion might prevent civilizations from expanding beyond their home planets. The easily accessible fossil fuels that powered humanity's industrial revolution are finite, and won't be available for any future civilization that might arise on Earth after us. Without this energy bootstrap, developing space technology might be impossible. Civilizations might invariably consume their planet's resources before developing sustainable space-based infrastructure, trapping themselves in a gravity well they can never escape. The doomsday argument, developed by philosophers including Brandon Carter and John Leslie, uses Bayesian reasoning to suggest that humanity is unlikely to expand into a vast future civilization. If humans were randomly selected from all humans who will ever live, we would be extraordinarily unlikely to find ourselves among the first tiny fraction if trillions of humans will eventually exist. The fact that we exist now, relatively early in technological development, might suggest that few humans will exist in the future, implying an approaching filter. However, this argument faces numerous criticisms and counterarguments. The reference class problem questions whether we should consider ourselves randomly selected from all humans or from all conscious observers, drastically changing the calculation. The self-indication assumption suggests we should update our probability estimates based on our existence, potentially canceling out the doomsday argument's pessimistic conclusions. These philosophical debates highlight the difficulty of reasoning about observation selection effects and anthropic principles. The transcension hypothesis offers an alternative to traditional great filter scenarios. Perhaps advanced civilizations don't expand outward into space but inward into increasingly small scales, pursuing computational efficiency and virtual realities rather than physical expansion. They might compress themselves into black holes or quantum computational structures, becoming undetectable to outside observers. This inward turn might be a natural attractor for intelligence, explaining the empty universe without requiring extinction. The zoo hypothesis and related ideas suggest that the filter might be artificially imposed rather than natural. Advanced civilizations might quarantine emerging species, preventing contact until they reach sufficient maturity. This coordinated isolation would require remarkable cooperation among independent civilizations but might explain the Great Silence. The filter would then be a test of worthiness rather than a natural obstacle, with contact awaiting our successful navigation of current challenges. The rare Earth hypothesis, elaborated by Peter Ward and Donald Brownlee, argues that simple life might be common but complex life extraordinarily rare due to numerous required coincidences. Earth's large moon stabilizes our axial tilt, preventing extreme climate variations. Jupiter shields us from excessive asteroid impacts. Plate tectonics regulates climate through the carbon cycle. Our Sun's unusual stability avoids harmful radiation variations. The galaxy's spiral arms trigger periodic mass extinctions that drive evolution without completely sterilizing the planet. Perhaps the combination of all these factors is so improbable that Earth is unique or nearly unique in hosting complex life. Anthropic selection effects complicate our reasoning about the Great Filter. We necessarily observe ourselves in a universe compatible with our existence, which might not be representative of typical universes or typical planets. The observer selection effect means we cannot draw strong conclusions from our single data point. We might exist in an extraordinarily rare pocket of habitability in a mostly lifeless cosmos, or we might be typical of countless civilizations we cannot yet detect. The simulation hypothesis adds another layer to Great Filter considerations. If we live in a simulated universe, the absence of alien civilizations might reflect computational limitations or the simulator's purposes rather than natural filters. The simulation might be designed to study isolated civilizations, making contact impossible by design. Alternatively, we might be approaching the simulation's boundaries, with the filter representing the limits of what the simulators choose to compute. Recent discoveries have informed our understanding of potential filters. The detection of phosphine in Venus's atmosphere, though disputed, raised the possibility that life's origin might not be the filter if it arose independently on a neighboring planet. The discovery of extremophiles in Earth's most hostile environment suggests life is remarkably adaptable once established. The rapid appearance of life on Earth after the late heavy bombardment implies that given suitable conditions, life emerges readily. The discovery of complex organic molecules in space, including amino acids in meteorites and organic compounds in protoplanetary disks, suggests that life's building blocks are common throughout the universe. This ubiquity of prebiotic chemistry might indicate that the filter doesn't lie in life's origin but in some later evolutionary step. Alternatively, the step from complex chemistry to self-replicating life might still be the crucial bottleneck despite readily available materials. The implications of the Great Filter's location profoundly affect humanity's future prospects and priorities. If the filter lies behind us, we are extraordinarily precious, possibly the only technological civilization in the observable universe. This cosmic loneliness would make humanity's survival paramount, as we might represent the universe's only opportunity for self-awareness and exploration. Our expansion into space becomes not just desirable but a cosmic imperative. If the filter lies ahead, identifying and avoiding it becomes humanity's most critical challenge. We must carefully examine potential extinction risks and develop robust strategies for navigating them. This might require fundamental changes in how we organize society, develop technology, and expand into space. International cooperation, long-term planning, and careful risk assessment become essential for successfully passing through the filter. The search for extraterrestrial intelligence directly informs our understanding of the Great Filter. Finding simple life would suggest the filter lies after life's origin. Discovering complex but non-intelligent life would place the filter at or after the evolution of intelligence. Detecting ruins of dead civilizations would strongly suggest the filter lies ahead of us. Only finding thriving advanced civilizations would indicate that no insurmountable filter exists, though their absence so far suggests this optimistic scenario is unlikely. As our search for life continues with increasingly sensitive instruments and expanded search strategies, each null result adds evidence for a strong filter somewhere in the evolutionary chain. The continued silence of the cosmos, despite decades of searching and thousands of known potentially habitable planets, suggests that at least one step from non-living matter to detectable civilizations is extraordinarily difficult. Understanding which step represents the filter remains one of the most profound questions facing humanity, with implications that extend far beyond academic curiosity to the very survival and cosmic significance of our species. The exploration of the Great Filter concept ultimately returns us to fundamental questions about humanity's place in the universe. Are we alone, the sole witnesses to the cosmos's grandeur? Are we the vanguard of intelligence, among the first civilizations to arise in a universe destined to bloom with consciousness? Or are we latecomers to a cosmos already populated with intelligence we cannot yet detect or comprehend? The answer shapes not just our scientific understanding but our philosophical, ethical, and practical approaches to the future. As we reach the end of our cosmic journey through humanity's search for extraterrestrial life, we find ourselves standing at an extraordinary moment in this ancient quest. The question that our ancestors pondered while gazing at the stars has evolved from philosophical musing into rigorous scientific investigation, employing instruments of remarkable sensitivity and techniques of stunning sophistication. Yet despite our technological prowess and expanding knowledge, the cosmos maintains its profound silence, neither confirming nor denying the presence of other minds contemplating their own existence among the stars. The search for alien life has transformed dramatically from those first wanderings of ancient civilizations to today's systematic surveys and targeted observations. We've progressed from mythological speculation to mathematical frameworks, from imagining inhabitants on the moon to detecting potentially habitable worlds orbiting distant stars. Each advancement in our understanding has paradoxically both brought us closer to an answer and deepened the mystery, revealing a universe far more vast and varied than our predecessors could have imagined. The discovery of exoplanets has shown us that worlds beyond our solar system are not rare exceptions but the norm, with planetary systems exhibiting architectures that challenge our theories and expand our concepts of habitability. We've found planets in places we thought impossible, orbiting binary stars, surviving near pulsars, wandering freely through interstellar space. The universe, it seems, is remarkably creative in its planet-making, suggesting that if life can exist, it has countless stages upon which to perform. Our understanding of life itself has undergone radical revision through the discovery of extremophiles thriving in conditions that would have been considered utterly hostile just decades ago. These organisms have taught us that life is more adaptable, more resilient, and more creative than we ever suspected. The boundaries of the possible have expanded so dramatically that we must now seriously consider life in the subsurface oceans of icy moons, in the upper atmospheres of Venus-like worlds, perhaps even in the exotic chemistry of Titan's hydrocarbon lakes. The development of SETI from a fringe pursuit to a mainstream scientific endeavor reflects our growing technological capability and deepening cosmic perspective. Modern searches employ instruments that can detect the equivalent of airport radar from dozens of light-years away, analyze billions of radio frequencies simultaneously, and identify patterns that might indicate artificial origin. Yet the null results so far obtained are themselves profoundly informative, constraining the prevalence and nature of technological civilizations in our cosmic neighborhood. The philosophical implications of our search extend far beyond the scientific questions. The possibility that we might be alone in the observable universe carries weight that transcends academic curiosity. If Earth harbors the only known life, if human consciousness represents the universe's sole example of self-awareness, then our responsibilities multiply enormously. We become not just one species on one planet, but the carriers of something precious and possibly unique, the ability of the cosmos to know itself. Conversely, the discovery of life elsewhere, whether microbial or intelligent, would fundamentally alter our cosmic perspective. Finding even simple life on Mars or in the subsurface ocean of Europa would suggest that life emerges readily when conditions permit, implying a universe teeming with biology. Detecting signals from an alien civilization would provide the ultimate mirror for humanity, forcing us to see ourselves from an outside perspective for the first time in our species' history. The Great Filter concept haunts our considerations, suggesting that somewhere between non-living matter and galaxy-spanning civilizations lies an almost insurmountable obstacle. Whether this filter lies in our past, making us extraordinarily fortunate, or in our future, warning of challenges ahead, remains unknown. Our search for life elsewhere directly informs this question, with each discovery or non-discovery adjusting our estimates of where the bottleneck might lie. The technological challenges we face in detecting alien life push the boundaries of human ingenuity. We're developing telescopes that can analyze the atmospheres of planets light-years away, designing probes that can explore the subsurface oceans of icy moons, creating artificial intelligence systems that can identify patterns in vast datasets that human minds could never process. These technologies, developed for the search for life, advance human capability in countless other domains. The search has also revealed the importance of time in cosmic considerations. Civilizations might rise and fall in cosmic eye blinks, their brief flickers of radio emission passing Earth before humans evolved or after we've gone extinct. The synchronicity problem, the need for civilizations to exist not just in the same galaxy but at compatible times and technological levels, adds layers of improbability to contact. We might live in a universe where intelligence is common but contact is rare, ships passing in the cosmic night. Climate change, nuclear weapons, artificial intelligence, and other existential risks take on new significance when viewed through the lens of the Great Filter. These challenges might represent universal tests that all technological species must navigate, with failure resulting in extinction or permanent limitation. Our success or failure in addressing these challenges might determine whether Earth's intelligence spreads to the stars or remains forever confined to one world. The cultural impact of the search for extraterrestrial life extends throughout human society, influencing our art, literature, philosophy, and dreams. Science fiction explores the possibilities, preparing our minds for contact scenarios ranging from benevolent teachers to existential threats, from incomprehensible aliens to beings remarkably like ourselves. These stories serve as thought experiments, allowing us to explore the implications of contact without the immediate consequences, preparing our collective psyche for possibilities we might someday face. The search has become a mirror for humanity's hopes and fears, reflecting our deepest anxieties about loneliness and our greatest aspirations for cosmic community. Every generation projects its own concerns onto potential aliens. From Cold War fears of invasion to modern hopes for technological salvation from climate change. The aliens we imagine reveal more about ourselves than about any actual extraterrestrial beings, serving as a canvas upon which we paint our dreams and nightmares. Educational initiatives inspired by the search for life have introduced millions to astronomy, biology, and the scientific method. Programs like SETI at home have democratized participation in cutting-edge research, allowing anyone with a computer to contribute to humanity's greatest quest. School children learn about extremophiles and exoplanets, growing up with a cosmic perspective that previous generations could hardly imagine. The search for life has become a gateway drug to scientific literacy, inspiring careers in fields that will shape humanity's future. International cooperation in the search for extraterrestrial life provides a model for addressing global challenges. Scientists from nations that might be political adversaries work together, sharing data and insights in pursuit of a common goal. The search reminds us that national boundaries are arbitrary lines on one pale blue dot, insignificant in the cosmic context. If we detect an alien signal, humanity will need to respond as a species, not as competing nations, forcing a level of cooperation we've rarely achieved. The protocols developed for handling potential contact, though never tested, represent humanity's attempt to prepare for the ultimate unknown. These agreements, debated by scientists, ethicists, and policymakers, address questions we hope to face: who speaks for Earth? How do we decode an alien message? Should we respond, and if so, what should we say? The mere existence of these protocols represents a maturation of our species, an acknowledgement that we must think beyond our individual lives and immediate concerns. The economic implications of the search, though often overlooked, are substantial and growing. The technologies developed for detecting biosignatures and technosignatures find applications in medicine, communications, and environmental monitoring. The space industry, partly driven by the search for life, generates hundreds of billions in economic activity while pushing the boundaries of human capability. Investment in astrobiology research yields returns not just in knowledge but in practical technologies that improve life on Earth. Religious and spiritual perspectives on extraterrestrial life have evolved considerably, with many traditions now embracing the possibility of cosmic neighbors. Theologians contemplate the implications of alien souls, the universality of consciousness, and humanity's special or ordinary place in creation. The discovery of alien life might challenge some beliefs while confirming others, forcing a reconsideration of humanity's relationship with the divine and our responsibilities as potentially one among many intelligent species. The psychological impact of the search affects us even in the absence of detection. The possibility that we might not be alone provides comfort to some and anxiety to others. The cosmic perspective gained from contemplating our place in the universe can be both humbling and empowering, reminding us of our insignificance while highlighting the preciousness of consciousness. The search for life becomes a search for meaning, a way of understanding our purpose in a vast and ancient cosmos. As we look toward the future, the search for extraterrestrial life stands poised for potential breakthroughs. The James Webb Space Telescope is analyzing exoplanet atmospheres with unprecedented precision. Future missions will directly image Earth-like planets and search for biosignatures in their reflected light. Advances in artificial intelligence will enable us to process vast amounts of data, potentially recognizing patterns we've overlooked. Each technological advancement brings us closer to answering the ancient question. The possibility of discovering life in our own solar system grows more plausible with each mission. Europa Clipper will investigate Jupiter's ocean moon in unprecedented detail. Dragonfly will explore Titan's organic chemistry. Future missions might drill through Europa's ice, swim in its dark ocean, and search for life in an alien sea. Mars sample return will bring pieces of another world to Earth's laboratories, where we can search for ancient Martian life with our most sophisticated instruments. The development of interstellar exploration capabilities, though still in early stages, suggests that humanity might someday search for life not just with telescopes but with direct exploration. Breakthrough Starshot's tiny light-sailed probes could reach nearby stars within decades, sending back close-up images of potentially habitable worlds. Future technologies might enable even more ambitious missions, perhaps carrying artificial intelligence or even humans to the stars, transforming us from observers to explorers of other solar systems. The ethical considerations of our search continue to evolve as our capabilities expand. Should we actively transmit messages to attract alien attention, or does that pose an existential risk? If we discover microbes on Mars, how do we balance scientific investigation with planetary protection? If we detect a signal from a dying civilization, do we have obligations to preserve their legacy? These questions force us to develop ethical frameworks that extend beyond Earth, considering our responsibilities as cosmic citizens. The search for extraterrestrial life has taught us patience on cosmic timescales. We've learned that the universe operates on timescales that dwarf human experience, with processes unfolding over millions and billions of years. Our search, spanning less than a century of serious effort, represents the briefest beginning of what might be a multi-generational or even multi-millennial quest. This long-term perspective, forced upon us by the cosmos's vast scales, might prove essential for addressing challenges like climate change that require thinking beyond immediate gratification. The transformation of our understanding continues accelerating as new discoveries reshape our cosmic perspective. Each exoplanet detected, each extremophile discovered, each null result from SETI searches adds to our growing picture of life's possibilities and limits. We're assembling a vast puzzle without knowing the final image, each piece revealing a bit more while often raising new questions. The search for life has become humanity's greatest detective story, with clues scattered across the cosmos waiting to be discovered and interpreted. The possibility that we might create artificial intelligence that surpasses human intelligence adds a new dimension to our search. Such intelligence might be better suited to recognize alien signals, decode messages, or even conduct the search itself over timescales that would frustrate biological beings. We might be in the process of creating our successors in the search for cosmic intelligence, entities that can think on astronomical timescales and perceive patterns invisible to biological minds. As our own technology advances, we're beginning to understand what technosignatures we ourselves produce and how they might appear to distant observers. Earth's radio leakage, city lights, industrial pollutants, and climate modifications create a detectable signature of technological civilization. This self-awareness helps us understand what to look for elsewhere while also raising questions about whether we want to be detected. We're simultaneously searchers and potentially the searched for, hunters who might also be prey. The convergence of multiple scientific disciplines in astrobiology has created a new way of doing science, breaking down traditional boundaries between fields. Astronomers work with biologists, geologists collaborate with computer scientists, and philosophers engage with engineers. This interdisciplinary approach, necessitated by the complexity of searching for life, provides a model for addressing other complex challenges facing humanity. The search for life has taught us that the biggest questions require diverse perspectives and collaborative efforts. The role of private funding and entrepreneurship in advancing the search represents a shift from purely government-sponsored research to a hybrid model that might prove more sustainable and innovative. Billionaire philanthropists funding SETI research, private companies developing space exploration technologies, and crowd-funded research projects demonstrate growing public engagement with the search. This democratization of space exploration and astrobiology research might accelerate progress while ensuring continued support regardless of political changes. The search for extraterrestrial life has revealed the importance of planetary protection, both protecting Earth from potential contamination by alien organisms and protecting other worlds from contamination by Earth life. These protocols, developed through international cooperation, represent humanity's attempt to explore responsibly, acknowledging that we have obligations to preserve other worlds for future study and potential indigenous life. This careful approach might slow exploration but ensures we don't inadvertently destroy what we're searching for. The communication challenges posed by potential contact have sparked innovations in linguistics, mathematics, and information theory. How do we communicate with beings that might perceive reality completely differently, operate on different timescales, or think in ways utterly foreign to human cognition? These questions push us to develop more universal forms of communication, based on mathematics and physics that should be consistent throughout the universe. The work on interstellar communication might ultimately help us communicate better among ourselves, bridging cultural and linguistic divides on Earth. As we contemplate the vast silences between the stars and the apparent absence of obvious alien civilizations, we're forced to confront the possibility that intelligence might be extraordinarily rare or fleeting. This cosmic loneliness, if true, makes Earth's biosphere and human consciousness incredibly precious, perhaps unique treasures in a vast, unconscious cosmos. The responsibility this places on humanity is staggering, suggesting that our survival and expansion into space might be not just desirable but essential for consciousness to persist in the universe. Yet the search continues with undiminished enthusiasm and ever-improving capabilities. Each generation of scientists builds upon previous work, developing new techniques and exploring new possibilities. Young researchers entering the field today might witness humanity's first contact with alien life, whether microbial or intelligent. The questions that have haunted humanity since we first looked up at the stars might be answered within our lifetimes, transforming our understanding of our place in the cosmos. The search for extraterrestrial life ultimately represents humanity at its best, curious, persistent, collaborative, and hopeful. It embodies our refusal to accept ignorance, our determination to understand our cosmic context, and our hope that somewhere among the stars, other minds might share our wonder at the universe's beauty and complexity. Whether we discover alien life tomorrow, in 1,000 years, or never, the search itself ennobles our species, pushing us to transcend our limitations and reach toward the infinite. As you drift off to sleep tonight, perhaps you'll dream of distant worlds where alien beings contemplate their own night skies, wondering if they're alone. Perhaps they too search the cosmos for signs of intelligence, sending signals we haven't yet detected or recognized. In the vast darkness between the stars, countless worlds orbit their suns, each potentially harboring wonders we can barely imagine. The universe's greatest mystery remains unsolved, but each day brings new discoveries, new possibilities, and new hope that we might finally answer the question that has defined our cosmic journey. The story of humanity's search for alien life continues to unfold, written not in any single discovery but in the accumulation of knowledge, the development of technology, and the evolution of our cosmic perspective. We are all participants in this grand adventure, whether as scientists analyzing data, citizens supporting research, or dreamers contemplating the possibilities. The search for life beyond Earth is ultimately a search for understanding, meaning, and connection in a cosmos whose scale and age humble our imaginations. Thank you for joining me on this gentle journey through humanity's quest to find our cosmic companions. As you close your eyes and let sleep embrace you, remember that you are part of the first generation in Earth's history capable of scientifically searching for life beyond our world. The universe's greatest secret might be revealed in your lifetime, transforming everything we thought we knew about our place among the stars. Sweet dreams, and remember to keep looking up, for the cosmos holds wonders yet undiscovered, mysteries yet unsolved, and perhaps, somewhere in the vast darkness, neighbors yet unmet. If you enjoyed this cosmic journey through the search for extraterrestrial life, please consider liking this video and subscribing to the channel for more explorations of the universe's grandest mysteries. Your support helps us continue bringing the wonders of space and science to fellow dreamers and stargazers around the world. Until next time, this is Sleepy Parallax, wishing you peaceful dreams among the stars.